Hey,
Hey, what's up?
it's just a meeting us today.
Yeah. Ah, seems to. How
Yeah,
are you
pretty
doing?
excited. Pretty good, pretty good. Pretty excited about this week. Although yesterday the class was like, what?
Yeah, I didn't understand anything.
Yeah.
It was like so much throwing it toward us.
Yeah, I was expecting it to be, well, we talked about like TCP, UDP, and these kind of IP, and I thought it was going to be just kind of like only this, making networks, but it was
Yeah,
way more than this.
yeah, it was super vast. Like,
Yeah, yeah.
and I was just hearing just alphabets, like
Yeah,
C, B,
literally.
C,
I was
C.
thinking,
What is
if you
this?
take a snippet of the video of him for like a sentence or two, you must be like, what? Yeah, it's quite
Yeah, but it was cool. I don't know what we are gonna do. It would be amazing if we could manage something like for the group assignment. So we can set up I don't know, like an MCU node, each of us, and then share the
We should
IP.
somehow share the Zoom link every
Yeah,
like a network of sharing Zoom links.
yeah, maybe like we just connecting to that MCU and it's kind of just constantly
Yeah.
updating the MCU, like the Zoom link.
Uh,
Would be amazing.
yeah. But yeah, I mean, there's the simplest thing of switching a lamp on, which is or an LED or something. But that'd be yeah.
Yeah.
Maybe we can have a little brainstorm this afternoon as well as we're having this call. The call about it. Why is it recording the thing?
No, it's the setup of the Zoom. So Ayak set up the Zoom links in a way that whenever you click on it, everything is recorded and it's uploading in a cloud.
Yeah.
So
But why there's two of us now? Ah, there's Vitaly.
yeah,
Hola.
hello. Maybe we can just carry on by
So
ourselves,
I'll start the class.
self-talking.
Yeah. So if you go to the book, chapter 24. Actually, let's see if there's the class up. I was
Yeah,
thinking to
I guess there is a link of the class.
networking and communication.
Morning.
Good morning. Yeah, there's a class. But it's weird, there's nobody else. I wonder if there's another link somewhere. There's only like 5. There's Rouget. Yesterday, Rouget, when it was your turn, I don't know if he's hearing. Are you here, Rouget?
I guess he's trying to connect.
Yeah, because there's no microphone or camera. But yes, yeah, I had him out. So.
Yeah, I heard it. It was funny. Ben, did you
Yeah.
manage the grasshopper thingy?
I
How's
haven't. I
looking?
haven't tried again. I haven't tried more. I'm still.
Okay.
I need. I need to. I'll do this at some point. I mean, the worst case, I can just if I want to actually. I want to get a little. I wanted to get it done so I can have somebody to cut it in like little cardboard at the office.
Yeah.
Because I'm trying to think of like systems to do the automatic watering, but it's like with my sketches, it's kind of like hard to see because if you want to water, you need a certain height, so the water may like it's kind of hard to see. So I want to have it made
Yeah.
physically, and I can see it, can I look around and stuff.
Yeah. True.
Rouget, Rouget, are you here?
Yeah. Now he's here, but
He's
he's not.
alive.
Morning.
Good morning, Oscar.
How are you guys?
Good morning. Good. How are you?
Good.
All good. Prepping my coffee.
With avena coffee, avena milk.
Ah,
With avena milk.
Avename.
Avena, oat milk. Yeah, Rouge, yesterday when it was your turn, Neil said, Roger? And then I told him, I was like, yeah, he's going to tell you to call him Rouge, but he didn't answer, so.
Hello, good
okay.
morning, everybody.
Good morning.
How was yesterday class with Neil?
Overwhelming.
Yeah, fucking
Overwhelming.
hell. It's just
Why?
letters. It's just the letters.
Yeah, it's like alphabet throwing us like
Yeah.
what he's talking about.
And do you think so
Yeah,
today?
I to see many things.
Worse than ITC. ITC is the one we're familiar with. It was the other ones, the problem.
SPI.
Everything else. Especially, what was it? There's when we did the, what was it? Oh yeah, the modulation, PCM, PPM, OK, FSK, BPSK.
That is very nice. FSK and AFSK is super cool to make communication with audio. It's we tried to do that a long time ago. Like you send pulses with sound, and depending on the frequency of those of the sound, you are sending one thing or another. So
I was wondering, because you know what I told you yesterday, where I want to have like this kind of thing talking to this over there. But the only thing I want, it doesn't need to be clever talking. I just need something to kind of say I'm on, and the other thing to know that the other thing is on. So I was thinking it doesn't need to send any clever data. It just needs to be like, oh, something is emitting on this frequency without having to say, you know, like, oh, I'm doing this. So I was wondering if we could do it with like ultrasound or just do it with some like something. I don't know. I'd like to make some homemade radio antenna.
That would be. Well, Edo is going to teach you today how to make antennas. That is very cool. But you could do your own transfer protocol, and that would be super amazing. Like if you manage to do a communication thing either with audio or ultrasound or light, like infrared or this type of thing, that would be really nice. And then you define how you transfer things and what means each of the statuses and stuff. It would be very good. So let's wait till Edu arrives.
Yeah, Oscar, which is the protocol that you use in the Smart Citizen to program it through the let's say light?
It was something that Victor made.
Maybe you can summarize this thing.
Yeah. So Smart Citizen sensors. Well, I don't think I can show you anything, but like the version 1.5, we're now in version 2.1. Version 1.5 was programmed or was configured with the light sensor. So it was super cool because you had in the screen, you had a square that was sending white or black pulses to the light sensor, and that was like the information codified in light, and the light sensor was reading it on the other end. So for example, when you configure the Smart Citizen, you have to tell it the Wi-Fi network of your home, the password, and let's say a small ID, so that the data gets to the server and knows what sensor it is. And that information was sent like that. And you just basically put the sensor in the screen, and the screen was turning black, gray, white, whatever in, I think it was a 15 or 16 different colors, but all of them in white or black and white scale. And the information was transferred like that. And Victor made like the whole calibration for it and everything. So it was super cool to just go to a workshop and configure your kit, and then the screen was doing this funky thing. And then you just put the kit in there, and magically, without any weird Wi-Fi or cable or anything, it was all configured. And then we tried to do the same, but with audio. So your computer will do like, and that was the information. Basically, each of the frequencies would mean a different byte or a different character, and the microphone will listen to that and store it in the configuration, which is something that you of course can try. And if you make that, I will love you forever, because it's super. I mean, it's like a very, you do it your own thing, you know, not relying on cables or anything like that.
So you throw them a challenge, isn't it?
That's a
At the
challenge.
same
I hope
time,
that
But let me
someone
see. Did you success with the sound?
we stopped doing it with the sound because just by while we were doing it by Wi-Fi, at the end we improved. Well, Victor improved so much the phone, like the configuration with the phone, that it was super fast. And then we didn't explore it anymore. But it's some of those things that will always remain there. I have the code I was prepping and everything to generate the sequence and stuff. So if anyone is interested, I have quite a bit of research into that.
Okay, cool. Anissa, you didn't get anything. Is it what you are telling me?
Yep.
But I think so. I mean, I think so. Some of you already received the components.
Yeah, Cesar, for example, not components. He already get the Arduino kit, the one you sent. So that's why I'm asking. Maybe
I will check it. I mean, as I know, they ordered it probably as we ordered from different like suppliers, let's say. So some of them are.
Okay.
It takes more time than another ones.
So.
But I will remind like Vanessa to follow this one. That because in your case it was the breadboard, isn't it, or something like this?
Yeah, it was breadboard. Also, I miss the cable from
the jumper cables.
Yeah, so I can't even connect my Arduino to laptop.
Okay, I will take a look. Okay.
Thank you.
Santi, should we mention a little bit about planning for tomorrow?
Yeah, for sure. No, you should.
Okay, so overall planning, we will repeat this during the session today. So today we're going to have a more theoretical class, trying to understand two very big groups of communication: wire communication and over-the-air communication. I will do wire part, and Edu will do over-the-air part. So there will be like the whole class on it. The documentation is already online and everything. And tomorrow we will do a hands-on session. So for that, what we will do tomorrow is that we will build a network, a remote network, with all of you sending data to a Raspberry Pi that I have on my desktop, and we will receive the data and plot it is like a sensor data or whatever you want to send, and put it in a dashboard. But it will be done remotely. So for that, you need one of these two things: either Arduino or similar, a chip with Wi-Fi connectivity like a ESP8266, ESP32, or something like that. Option one. And option two is a normal Arduino that you can connect with cable to your computer, and that your computer can execute a Python code or similar, so that your computer sends stuff to me. So option one, Arduino or similar. Option two, normal Arduino without network connectivity and a computer that can run code like something like Python. And I will prep the scripts and send them to you. And today as well, I will send this email for you guys, but you will need to know the server that we have configured, and the like some topics that we will use for tomorrow. So all these details will be in the email, so check them during the afternoon. Okay, and try to make sure that tomorrow in the morning you have everything ready. The idea is that we are going to be like this, but we're not going to talk that much. The idea is that you send us stuff over the network, and then we try to solve problems little by little. Maybe we can even just have like dedicated chats or something, but it's more like a hands-on session. So if you're if you don't have things ready for Python or this type of things, try to invest some time if you want to come tomorrow. Okay.
Yeah. The good thing is that if you participate in the tomorrow session, probably you will almost done that week, especially for the MDF.
It will be totally done, exactly. So if you do this week and you explain and you document it on your website, then the assignment is done. So at 2 p.m. tomorrow, if you come to the session, you are done for the week. Hello.
I'm not sure, but I think we have class tomorrow at 2.
No,
you said 2.
You have class tomorrow at 2, and the class will be from 10 to 1, more or less.
Ah, okay. Sorry. Yeah, I don't know why I'm still sleepy.
No,
sorry. I meant like at 2 it would be done. Like you would have the assignment done. I mean.
Yeah. Okay, perfect. Thank you.
Maybe Oscar, you can also explain the Guillem, or at least.
Okay. Yeah. Sorry. And also on Tuesday morning, there is an optional class about OSI model. OSI is the structure that network topologies over the internet use, and it's quite a complex thing that is very, well, not complex thing, is a little bit more advanced stuff. And then you will learn all these things about what is TCP, IP, UDP, all these things that everyone talks about on the internet, and these things that sound a little bit like Chinese. Guillem will give a class on that from 10 to noon on Tuesday, and we will put it on the calendar. And it's going to be a master class as well. So it's like a very interesting class about these things. And I don't know if we have done this previous years, but for sure it will be super interesting.
Okay.
Oscar, in any of those today, tomorrow, or the Tuesday classes, are we gonna know a little bit more about MQTT and Node-RED?
Tomorrow you will learn everything about that.
Okay, perfect. Thank you.
Then the session for tomorrow will be using Node-RED and MQTT, and you will be. Okay. I made a Node-RED dashboard in the Raspberry Pi and MQTT broker, and you will be sending that to me, and you will use MQTT to send it.
Okay, thank you.
Yeah, guys, this week is a very nice week. You will love it. It's when the things becomes interesting. No, because now everything will get interconnected, you know. It's like a little bit more crazy, but it's okay. Vale, pues tíos, vosotros mismos, ¿eh?
Okay, so let's start. Let me start sharing my screen. We are recording, so okay, do you guys see my screen?
Yes, we do.
Perfect.
It's very nice.
Very nice, my screen. Okay, so today's class is about networks. In the, as usual, in the local documentation, you have the classes. Here, today we were going to talk about wired and over-the-air communications. The first part of the class, I will be mostly, it will be myself teaching about wired communications, and the second part of the class, Edu, will teach about over-the-air networks, okay? Tomorrow, as we said, we're gonna do the hands-on session in which you will be, like all of us, we will be sending data over MQTT to a server that I have at home, and we will try to make a whole network with you guys. So for today, this is the documentation. And as I said, we're going to start with wired communication. Important to know some clear things, and where this is going to be a class of like distinctions, like one versus another. The first of them is wired communication versus over-the-air communication. Wired communications are meant for short distances, very short distances, like within a device or within devices that have like the distances between them of the range of a table or a desktop or something like that, but nothing super big. The most ideal case is that you have different chips in the same board and you transfer and you make them talk to each other. For example, already you have communication between your FTDI chip and your ATtiny or your ESP32 or these type of things over a protocol that is called serial. And we will talk about it in a second. But that is the range of communications that we want to talk about. Also, you have the same type of communication between your computer and the Arduino over serial as well, or over a protocol called the USB bus. Over-the-air communications, as Ed will say later, are meant more for, of course, longer distances and also independent devices, like things that can move and that don't have to be attached to a cable or to the same board. So clearly, the first distinction that you should make, whatever you're going to choose things to communicate to each other, is what's the distance between them and what's the physicality of them, if they are on the same board or not, and if they can be detachable or not. Then diving in a little bit into wired communication. The first distinction that we're going to make is how we send the data. This can be done in two ways. I could be sending data as I am doing right now to you in a serial way. So serial is one chunk of data after another. And as I'm talking to you, I'm sending one word after another, and I am transferring a message to you by sending serial words that are one after another to you, and you're hearing them and processing them. But there could be another way of transferring this. And for example, imagine that I transfer everything at the same time. Instead of saying each word and one after the other, I would tell you all the words at the same time, and you would have ways of listening to all of them at the same time and reorder them. So that's the idea. Serial communication is a way of transferring data in a sequence, and parallel communication is a way to send data in different buses, so that so that you receive the data in waves, let's say, and you receive more data at a time. Here it's clear, and you've probably seen this type of connector in the past, the RS232 or the parallel port, or these type of things that all machines and many industrial machines still use. And it's basically meant for high-speed things. When, of course, if you want to send data over a cable and you are sending data one after the other, the things are going to be slower than if you send everything at the same time. But of course, if you send data all at the same time, you need a lot of pins and a lot of cables to send in parallel. And that's why we have these type of connector topologies and the parallel cables and this type of things. If you look for parallel cable or this type of thing, you will see, and probably you have seen this in computer and these things, like this type of, especially this type of things, where all the cables are connected in parallel, and you have pins that are each of them dedicated to send messages, and the data is sent across the cable in all of them at the same time. Of course, if you increase, so for example, right now we don't see these type of things anymore, and probably I think that Juanita has showed an Arduino yesterday that had RS232 Arduino. I saw this in a picture yesterday. So, of course, these things still exist, and some Arduinos Uno at the beginning had this port, but now we have serial communication, for example, USB, that has only 2 lines and sends data in a sequence, so in serial way, that is very fast. So little by little, in older times, you saw these type of connectors more, and not anymore, because right now you use serial that is very fast and can cope with the differences of speed by, with reducing the number of wires. And that's basically what we do in this case. So in the example, in the case of serial interfaces versus this one, we are sending the data in sequence. And you see that this will be something that we will mention a lot during this class, is the clock. The clock signal is basically the director of the orchestra that is saying at which pace all the things have to be coordinated. So if we don't agree at the speed at which I am sending you the data, then it will be impossible for us to communicate. And if one side of the communication is expecting data to come very fast and the other side is sending it very slow, then there will be problems in communication. As you have already experienced this when you have serial communication in your Arduino, and then you basically receive garbage on the serial port. So that's one important distinction, serial versus parallel. And talking about the clock, that brings us to the next important distinction, which is synchronous communication versus asynchronous communication. What is the difference between them? Asynchronous communication, there is no clock signal. Means that the signals are sent just as they are, and both ends agree on how fast things should go. And that's, for example, when you connect your Arduino to your computer, both sides have to be talking at 9,600 watts, for example.
Oscar, can you blow up a little bit the page? Zoom in.
Yeah.
Make it a little larger, the text. Oh, thank you.
Is that better?
Yeah.
So this asynchronous communication is not caring about using a data line for the speed. You just have data transferred from one side to another, and you have to tell them, to the sender and to the receiver, okay, you both have to listen at this speed. On the other hand, in synchronous communication, you send a clock. And that's why you, for example, in I2C or some more complex protocols, there's a line dedicated for data and a line dedicated for clock. This clock is just a signal that is going up and down very fast and saying, like marking the pace at which you should expect changes in the data. So for example, in this case here, if I think it's an interesting exercise to just have a look at this schema and see how the data is received on both lines, just by having one signal that is going up and down always at the same time, and the other one that is going up and down transferring the data. So basically the signal in the top is saying, okay, when there's a rising edge, check what is the status of the data. And if it's up, then we have 1. If it's 0, if it's down, then it's 0. And basically you are transferring data by just transferring ones and zeros or voltages. And this is very important in information theory, is that when you send data over a network, what you are just sending is ones and zeros in the forms of voltage changes and nothing else. So basically you are putting a signal, a line, a cable, either to voltage or to ground, and you're doing that very fast. And believe it or not, that's how the whole world works right now. All the Ethernet and like the internet, everything is based on those simple principles, that just changing 0 to 5 volts in a cable, and that's it. You would have heard very likely one of the biggest cases or most important cases about asynchronous communication is WART or RxTX. And you have seen this in the Arduino. Arduino Uno.
Actually, you are all the time using this protocol when you connect to your computer, because what the FTDI chip does is translate the information from the serial of your computer and talk with FTDI to produce a serial RxTX signal that is connected to the serial AX of your IT-Tiny.
Exactly. So you have already designed your boards, and you remember that the Rx connects to TX and the other way and everything. So now we are going to understand why. You see here that this is these two pins in the bottom right part of the Arduino are they say in here Rx and TX, and this is basically a common way of calling serial communication, which is a type of asynchronous communication. Now we already know that. So we have it's serial and it's asynchronous. So asynchronous means that it doesn't have a clock, and serial it means that there's a sequence and you only need one cable. The thing is that so that you allow the host, so one side to send data and the other side to receive it, and vice versa at the same time, you just put two cables. And the idea is that you send data on one side from transmission side, and the other one receives it on receiving side, and the same on the opposite. And that's why you have to cross them. And you have done this already many times when you have your FTDI chip into your RxTX of your ESP32 or this type of thing when you have designed your board.
Sorry, why do we need to cross them again?
Because you have to look from the servers, from the chip side, that you only have one transmission and one sending and one receiving port. So data can only go in one direction on these pins. It's like one of them is set up as a digital input and the other one as a digital output. So and they cannot be flipped. So when you want to transmit data, you have to use the one that goes out, and on the other end, it has to be on the side that goes in, because if you connect transmission to transmission or sending to sending, it won't be read on the other end, because there's no way to go into the chip with the transmission one. And so that's why you send TX is transmission, but transmission can be bidirectional. So let's just say sending. So TX is sending out and receiving comes from transmission on the other side. Does that make sense?
Oscar, we saw that when we were making the schematics of the boards of the Arduino, right?
Yeah. Okay. Yeah, exactly. So in the Arduino, let's actually look at it very quickly. Arduino. Yeah. So Arduino. It's coming. Okay. So here you see your FTDI connector here, the one that you already know with the 6 cables. You know what ground VCC is, and there are 2 other lines, TX and RX. So TX, if we follow it, is connected to RX, because this is like if there was a chip in there, the FTDI chip, and that the transmission side, so the sending side of the FTDI chip has to be connected to the receiving side of the ESP32, and the same on the other side. So transmission side on the ESP32 has to be connecting to receiving side on the FTDI chip. That's a simple, like I'm sending communications, I'm sending words from my mouth to your ears, and you're sending words from your mouth to my ears. but you cannot send words from your ears to your ears, or from your ears to my ears. It's the same way. I cannot listen to you through my mouth somehow, if it does make any sense, you know?
So what you mean is like, sorry if I ask again, but that TX is always the one sending and RX is always the one receiving, or TX does both?
Yeah, no. So imagine that we live inside the ESP32, and we have the only ways of communicating with the outside is 2 pins. One pin is for sending data out, and that pin is the X, and the pin for receiving data is RX. And one is just goes out, and the other one just comes in, and there's nothing, and there's no other way with communicating using this protocol. So important here is that, again, data, there is no more to this, to serial or RxTX or serial communication than just this. So there are 2 cables, ground, but no clock, no nothing. And here it's very important that both ends are clear on how they are communicating. So that's why when you have you put serial communication in your Arduino script, you say serial.begin at 9600 bots, for example. Bots is the speed of the communication, and when you open your serial monitor, in the bottom right corner, you have to specify the speed at which you are receiving the data. Otherwise, you just receive like weird characters, right? That I think that all that has happened to you, all of you, at some point. And that's because the serial communication works just that way. Okay. You can read more. I'm not gonna go into the details of what it means, each of the details. If you're interested, there's a lot of documentation here and a lot of interesting links. But one thing that I want to talk about is called UART. So UART is the piece of hardware in charge of handling the serial communication. And when you look for information about this protocol in the datasheet, you won't find, you will probably find RxTX, but it will very likely come in this form. So UART. And it stands for Universal Asynchronous Receiver Transmitter. And sometimes you would also see it as USART, okay? Which is somehow like a hybrid way between asynchronous and synchronous thing. This you don't have to really care about. This is just for like a fancy picture. This is like a block diagram of a chip. And this is what like electronics engineers decide when they design a chip and what they want to put inside and the different modules that they have. So here you see, for example, that there are some pins going out and you have an ADC. For example, when you do an analog read and you read analog data from a sensor, you have the famous registers that you can access. You have, for example, regulators and stuff. And here, there's a bus. And here, there's a little block called USRT, which is the one that is in charge of this. So if you are looking, if your chip has possibility to talk with another one via UART or RxTX, you should look in the datasheet and check if they have it. However, some chips, they are so simple that they don't have it. Or sometimes you might need to have 2 serial communications and you only have 2 pins available for that. Like hardware pins that are available for that. So you could do something that is called software serial, which is using a library to use 2 pins on your microcontroller that are not initially meant by hardware to transmit as a serial communication and convert them via software to serve as a serial port.
Is that what bit banging is? Because he's always Niels is always talking about bit banging, and I'm never sure what he means.
Exactly. So bit banging basically is sending. Bit banging is not explicitly for this, but basically is using, let's say, just sending bits very fast on a pin by making very fast changes on the status on the pin, either up and down. And as we were mentioning earlier, it's as simple as that. We are just changing from 0 to 5 or from 5 to 0, and that means something already. And it's the same thing of, for example, we want to transmit, we want to send information or to transmit information of the status of a board, for example, and we can already tell when we put a power on LED. We can already know if the board is on if we put if there's an LED light up, and that is already in itself a communication protocol. Very simple one. We only have two options, either on or off, and we do it with light, but that is already sending me some information. And basically that's what we want, but we do it in ways that we don't see it, but we send it through cables, right? So when we implement this banking, it means that you are doing that thing very fast. So sending bits by changing the statuses of ports like high or low, and you do it in a way that is normally not meant, was not designed for that when you design the board. So the pins specifically are not meant as serial ports. You just take two other pins that you have unused, and you use them to send data over them. So this software serial thing, yeah.
But is there something actually special about the RxTX as a pins, or just a?
Well, so when you do yes, so let's go to this example. You all know this serial object in Arduino. This one that you have already done, like serial dot begin blah blah blah, and then serial print. Serial print is just sending a string of characters into the serial port in the two pins. When you do when you have serial, when you have a hardware serial already embedded into your chip, when you call serial, you're using that one, and that's a special thing about it. That already the chip knows in the board definition of Arduino that whenever we put this in an ATtiny, the serial port that we are referring to is the one that is implemented in the hardware, and that's it. That's a special thing about it.
It's not like faster or something. Like if it could be, it's the same. Okay.
No, it's the same thing. So the speed of that depends on how fast the chip can go, so the clock speed, and also the quality of the line. So for example, how, let's say, how short or long the lines are, and these type of things in the board itself. But in the chip, it doesn't change anything. So imagine that you want to communicate your Arduino Uno with a ATtiny to program it, for example, or you want to communicate an Arduino Uno with an ATtiny board that you have designed, but your Arduino Uno only has one serial port. How do you do that? You cannot connect into the serial port more than two devices. So one that is sending and the other one is receiving, and vice versa. You cannot hang from the same lines more things because they will get confused. So you need to define another serial port with by software. That's how we do that by using the library called software serial. So here there's an example.
Sorry,
software,
but what do you have in the example above two callings for serial, one serial and one serial USB?
Ah, yes, sorry. Okay. So some boards like the Arduino Zero have already two serials embedded by hardware. One of them is the normal serial and the serial communication in file, like this one, the one that you can have on the pins themselves. But you see that this board has two USB ports, and that is that this USB port is sharing the same serial as these two, and this other one is used for debugging. And this is a more complex board, but the idea is that you have two chips. The chip that you program with, and that where you're gonna put your code, and one chip that is somehow like vigilant, that is looking at the other chip and checking what it's doing. And you talk with this other chip with this USB board, and you basically use it to analyze how the code is executing and to polish your code and see the status of the variables and the registers and the memory and these things. This is more complex stuff, but each of them have a different name. And the way that this is done in Arduino is that we call this one serial, just serial, and the other one serial USB, and that's it. Okay. So if you are connecting to this port, you connect to serial USB. If you are connecting to this one, you use serial, and that's why we have both. We have both of them.
But I can still program the Arduino Zero through any of those ports, or specifically, okay.
Yeah, you can program through any of those ports if it's just a program. If you want to program, if it's just like a normal code. If you, for example, break something in the memory, or these more weird things that sometimes happen, that you like say brick your board, that is all of a sudden your chip is unused, then you have to use a programmer to program the board, and this port can be used for that. So you can use this chip to program this guy. Okay. And that is like a norm, like a more like a development type of board in which you already have two very big chips that have two USB ports and these things. But it's like it's like how you would start developing or testing things that you want to, for example, deploy and make like a product out of it or things like this.
So the Arduino Zero is better than the Uno.
Yeah, yeah.
Great naming.
They could have named it like Arduino 2 or something, but I don't know.
And it also seems to have more pulse width modulation inputs.
PWM, yeah. Because this chip, for example, is the same that the Smart Citizen has, is the SAMD21. You have this chip available in the Fab Academy inventory this year, and it is very powerful. So this chip can talk I2C, serial ports, whatever, and also has one protocol that we won't talk about today, but if you're interested, we can talk about it. It's called I2S, which is like I2C, but very fast, and it's meant normally for sound communication. So sending data or like sensor readings of a microphone, but at very, very high speed, like a high fidelity type of things, like 128 kilohertz or this type of thing. So high quality audio. So coming back to the example, serial, normal, the way that you already know. So for serial, we defined a serial port by software. And I really like, now I'm seeing this example, I really like when I see code in Spanish. It's very cool. So in here, what we're doing is we're creating an object called BT1. This could be whatever else we wanted. And we're using pin number 10 and pin number 11 to be used as RX and TX. So these are pins that you have available in your board, and you define them like this. And here we define when we begin the serial communication, and we use it as normal. So we can read or write from it as if it was a normal serial communication port. And as simple as that. Is just using two pins with the speed that you want. And these speeds, as you know, they have to be within a certain, they cannot be whichever speed you want. They have to be like 9,600, 1,100, 12,500, this type of thing. But then you can use them as you wish.
And you can't use the same baud rate between both. I saw that both examples have a different baud rate between the serial and the either serial's USB or the software serial.
Yeah, no, it's just random numbers. I mean, not like it's not like you have to use different or the same or anything. You can define it as you will. Things here, just to have in mind, is that things are more complicated when you transfer things fast. So you always have more chances of losing data when you increase the baud rate or the speed. And if some things don't work when you are talking with serial, the first thing to do, apart from checking the hardware, is check the speed and check that the speed is not too high, so that the communication happens effectively. And you have seen this, for example, when I don't know, showcasing one day when we were programming one ESP32 or something like that in one of the beginning when we were still in the Fab Lab, that it didn't work, and then I decreased the speed and it did work. And that happens only because you might lose 1 bit or something like that. That is important because you are sending data too fast, and you just decrease the speed, and then all the communications get sent, and everything is it makes sense for both sides.
Actually, that not only depends on the protocol, but it's something that we will go in the second part of the class, is like radio frequency communications, because it depends on frequencies, space, and where you are transmitting. So it's a software thing related on the protocols that you use to communicate, and also hardware related one.
But you are talking about, or you were talking about the serial communication speed or the software uploading speed? And another question, is there a way to do, okay. No, but I mean, there's one configuration when I'm uploading the software that I can put it in 11,000 whatever, but I know that the serial begin and the serial monitor have to be in the same. But
correct,
not
exactly.
uploading. The uploading can be different.
No, exactly. So one thing is, so there are two stages in there, right? One of them is that you're programming your board, and that happens at a certain speed, and you are transferring data, which is in this case the data is the code that you are flashing into the binary file, and you're sending that binary in with serial, and your computer already agrees with the Arduino at the speed at which you are going to send that code. And then there's the second stage, that is what we call the runtime, which is the communications that happen when your code is being executed. And that is, depending on the speed that you put in your code inside. But the speed that doesn't necessarily have to be the same speed as you used for flashing the code itself, which is an interesting thing, but it's like they are totally disconnected. One is one process flashing, and the other one is the runtime.
And is there any way to know the proper speed of the communication? I don't know, like a test we can run on terminal or whatever.
As far as I know, no. I mean, I don't know any, but very likely there are, like in development environments, there are or more serious development environments that the ones that I do. I'm sure that they have like these things implemented that you test and see, okay, am I receiving the data on the other end correctly? I send the data and then I receive it and I check if everything is fine, etc. But not that I know on my side.
So is there any recommendation of how we should do it? Like always starting 9,600 and start maybe going up? Or?
So for me, the most common one is this one, 115,200. And then if that works, great. If it doesn't work, then I start going down, like one step by step. And that's it, until you get a reliable communication. But of course, iterate over this and try to always debug it so that you think that you don't lose the communication in the meantime. One thing that I'm not talking about is one concept called CRC. So in this way, in this protocol, we don't have any way. It's not California resources. we don't have any way to know if the data was transferred or not. So CRC stands for cyclic redundancy check, and is a check that we do with our data, with the target, let's say, to see if we have if the target has received the data or not. What do we do with it? So the idea is that you are going to send a piece of data, like I don't know, a message that is that consists of 10 words, and you want to check if the data arrived or not. So imagine that we do, and I'm gonna share the whiteboard because I know you love it. So imagine.
You don't see.
You see it?
Yeah.
You see it now? Okay. So imagine that we send this message that is I don't know, made of 1, 0s, 1, whatever, right? And we want to know if that is sent from the sender, so TX out to RX, right? But we don't have any way of knowing if this was sent properly or not, because this guy will just receive it. But if all of a sudden it read 0.6 instead of 0.4 because the voltage was a little bit unstable or something, then we might get a 1 instead of a 0. So what we can do is make what we call a CRC checksum, which is, imagine that we made a mathematical operation to this piece of data, and we checked on both sides if that was sent properly. So we will do, for example, we're gonna sum the first and the last one, and we're gonna then send a message after this saying, okay, CRC check. My CRC check is 1. This guy sends the same CRC, and if they match, then it means that the communication was done successfully. And by that, we can do many operations in here. For example, it could be that we sum the first and the last. We make a sum of all of them. We sum alternating ones. We do a polynomial, like we take this one and multiply it by 2, and this one and we'll multiply it by whatever, and et cetera, and we make a unique number that both sides calculate, and this and this way we are able to check if whether or not the communication was done effectively. So you can read a lot about CRC if you want, but if you are interested about this, there's a very computer file CRC. I recommend you watch these videos in computer file, and if you are interested on these things. This guy, Professor Braceworth or something like that, is a guy in Berkeley, I think. You will see this gentleman, and he talks a little bit about all these things and how they were done in telegraph, sound, and these things, and how they are implemented at the moment in like cheap communications. I'll put the thing in the chat. So, okay. Oops, no, not that to everyone. Okay. So if you want to use this in Python, so serial, you already know, for those that come to the code club and stuff, you have heard of this, but this is just as simple as that. There's a library called PySerial. You just say import serial, you say which is the port, the baud rate again, you declare the object, and start reading data. And and that's pretty much it. So you can make a little Python code that reads data from your computer and from your Arduino, sorry, and then do something does something else. What you can do with this one as well, what we will do tomorrow is that for those that don't have a ESP32 or Arduino or things like that, and want to do the session tomorrow, have Python running, and I will send you a snippet of code so that you can read your data, like at least with some clues, and you implement that so that you can send data to me tomorrow. This is for the ones that don't have a Arduino or similar things for the hands-on session. Okay, finally, before we finish asynchronous communication, it's important to talk about USB. USB, do you see my screen again, right?
Yes.
Okay, just checking because sometimes this happens and then I keep talking and you just see at the whiteboard. So USB, USB is a like universal serial bus. So it's an implementation of serial communication with different or a special thing. And the special thing is that apart from the power lines, so USB ground and USB voltage is always 5 volts, we send data in 2 lines. It's not in one, but we send it in 2. But the data is differential between them. So the data lines have to always have a difference between them of at the maximum 3.3 volts. And the data is sent as the difference of these 2 lines. And that is called what we say a differential per circuit, which means that none of them is static. They can be at 5 or 10 or 0 volts or 3.3 or whatever, but it's the difference between them that sends the data. The difference in voltage between those 2 lines that send the data. That's why you have to put Zener diodes in the data lines on the FAB ISP and these things when you use the communication, because they cannot have a difference of more than 3.3. And basically, there is nothing special about it except the protocol and how you send the data and its structure inside, other than this, that you have 2 lines instead of 1 for sending the data inside. And you can implement this with a library called VUSB into some microcontrollers. But this library, as you can expect, is a little big sometimes, and it might require a big space on your very tiny memory in the microcontroller. So you have to be a little bit careful of what you put in there so that it doesn't take the whole memory. But even in ATtinies and some others, you can use this library to embed it and have USB connectivity in the microchip, and not only talk via serial or with an FTDI chip, but have USB directly inside the chip. And that doesn't always have to be, as you already know, that not all the boards that you've done, and they communicate with FTDI, but you could use this library to avoid that and talk with it via USB. A lot of tutorials and everything. I don't want to extend that much on them. If you're interested in this thing, start reading and clicking them and go as deep as you want in each of them. Yeah, so you know.
Hey, Óscar, I have a question. One thing is like the USB communication, but then also USB has like the profiles, you know, like keyboard, mouse, or MIDI or whatever. Like how does that relate like to the MIDI transmission? Like, is there like, does it have anything in common, or is that a completely different thing?
Okay, so USB devices, let's go into here, have something when you talk to them. If you go to if you have a Mac, or I don't know, I'm sure in something similar in Windows as well, you have these things like the USB device tree, right? For example, how does my computer know that what is on the other end is a keyboard and not a mouse? Because because of this data. Basically, the chips that are on the other end are able to tell you the product ID, the vendor. The product ID is basically what is it? If it's a product, if it's a keyboard, if it's a mouse, if it has an optical mouse, whatever. Who makes it? In this case, this means that it's Logitech. I have now, you know, the brand of my keyboard and the brand of my mouse. The version, the serial number, the speed at which it can go, and the current and some extra data. And that is within the chip. And when you connect something to your computer, they both send that information to each other, and your computer reads it and say, okay, what do I have here? Is it a mouse? Okay, does it need drivers? Yes. Where do I get these drivers? From here. I download them and stuff. How do you get these things? How do you get this product ID? Because not everyone, when you make a chip, you don't have it right away. You have to do a request for a product ID. And getting a vendor ID here. So you basically have to go to usb.org. They have a database of vendors and product IDs, and you have to do an application so that your device can be registered and put it into the database of usb.org, so that when you connect it to a computer or whatever else, it can be recognized automatically, and they can say, okay, this number that this thing is sending me correspond to Logitech, or to a mouse, or to a Raspberry Pi. Okay, and that's it. Does that answer your question, Bruno?
Yeah, mostly like what I'm thinking is like, you know, there's like some chips that have native USB implementation, and the others that doesn't.
Okay.
Like if we want to use USB, we need to use like BUSB, as you said. But like, could we do, for example, like show a device as a keyboard, for example, with any of those, like with the BUSB or the native, or does it have to have like something extra apart from being a native implementation that allows?
No, you could hard code that into your chip, and have a little thing that just shows up as a keyboard, and is just an AT-Tiny connected into it. The thing is, I mean, you could make a code and do it that way, but you cannot fake vendors, so you can end up into, I don't know if it's copyright infringement or whatever, but basically, if you sold it and you sold it as Logitech device, and you are Bruno device, that you can get sued for that, because Logitech paid for that membership into the USB.org, and you didn't, and you're using their vendor ID. But you can just hard code it into your device, and it will show up as anything you do.
And can we use the profiles without a vendor ID?
Yeah, you can just send the data. Like you can just have a hard coded things, and in principle, I think you shouldn't have any issue for that.
Okay, cool, thanks.
So just to clarify, another part of the question that you did is that some chips, as you see in here, I think this is a SAMD21 as well. They have USB already, like a small module inside that is USB 2.0 module that is going to talk with the outer world and exposing 2 pins to communicate directly with this block. And some chips don't have this, and some chips that do. And that is just a matter of the guys that the people that designed this the chip, they wanted to put it in or not. It's just a matter of cost at the end, like having different ranges of chips that have to do different things. Not everything has to connect to USB, although it seems like, but not everything. So that is there, and that's for asynchronous communication. do you how are you? Do you want to make a break, or should we make the break when we pause for the wired and we jump into over the air with Edu?
I guess between the two classes. How much longer is it?
Not that much longer. It's a lot of samples.
For me, I think I can wait to make the break after.
Okay. Okay. So then let's jump into synchronous communication. Important is that now we will need so the chips, they don't necessarily need to agree in the speed at which they are talking. In this synchronous communication, what we are going to have is normally what we call a master, which is the chip that is in charge of defining the clock speed, and slaves. And this is a little bit like I don't know, homophobic type of thing, but is the way it goes, and it's the terminology. Okay, so we have the director of the orchestra that is called the master, and the rest are slaves. So there are different types of protocols here. The first one is called I2C, and probably you know already a lot about it. And the other one is called, that we're going to see, is called SPI. There are differences between them, and we'll talk about them in a second. So I2C, it is a protocol that has 4 cables, voltage, ground for power, and then 2 cables for data. One that is sending actual data, and we call it SDA, and the other one that is sending the clock, and we call it SCL. Okay. The thing about it is that there can be what we call a bus, an I2C bus, at which a lot of things can be connected to it. And each of the devices that are connected to it, each of the slaves, will have an address. And that is the way that we will use to communicate to each of them independently. And we can have several masters, and we can have several slaves, and all that with 2 lines or 2 cables. And that's now you're guessing why it's so popular, because you have a lot of flexibility to use this protocol and use it, for example, for networks of sensors, of some networks of microcontrollers, and this type of thing. Now, the 2 data, so the 2 lines, SDA and SCL, cannot be managed by other than the master in principle, or the masters in principle. And the SCL is going to be the speed of the communication that the master decides, and just gonna put that line oscillating constantly at a certain speed, and the data is sent on the other line. And when we want to talk with someone, we call their name and we say, okay, LCD driver, I'm talking to you. And the LCD driver says, okay, I'm listening. Then the master says, okay, LCD driver, put these characters in the screen. And the other one says, okay, and that's it. And the rest of the things don't do anything. They just ignore that data because it was not addressed to them. Okay. Examples for this and the libraries that we will use in normal Arduino or big chips is called wire, as simple as that. The library is called wire, and you just start it like wire.begin. If you are the master and you are just receiving information, you don't need to specify the address. And you just say, okay, I want to request this number of bytes from the device number 8. And on the other side, you will have, let's say, the slave with the same address, in this case, number 8. And when there's a request, we will send a hello. So what's happening here is that we have one chip on one side that has the code on the top, and one chip on the other that has the code on the bottom. This code is for the master, and this code is for the receiver. And in the master, we don't need to specify any address because it's the guy that is just talking, and so everyone is listening to this chip. And it doesn't need to have any address of it.
Could you edit the page after to make receiver/master, because it's a bit confusing which one is which, or put in the code or something.
Okay. I will put
master as receiver. Okay, it's above. Sorry. Yeah.
Yeah. Sorry. Here is with this is clear.
Yeah, it makes sense. Yeah, I didn't see it.
Okay. So in here, what we do is we request data from device 8, and we want to receive 6 bytes. And we say, okay, while the bus is available, we want to read the data and print it. And that's it. And on the other side, what we're doing is we start the same thing, but we have to give an address. We have to say, okay, I am device number 8. And whenever I receive a request, you remember this concept of a callback, which is something that is going to be executed whenever something else happens. A function called request event is going to just send a hello. So this guy will, every 500 milliseconds, request data, and this guy is going to send that data back whenever it's requested. Okay.
Has the address of the sender has to be always a number, or it could be a name, like wire.begin Pablo?
In principle, it has to be an X number or a number that can be converted to something like an X. And I think, I'm not 100% sure, but I2C, I would have to check it, but it only can have up to 64, 2 digits of X, which is FF. So 256, yeah. So it's so you could specify that as an 8, or you could put like 0xFF, for example, or 04C, something like that. I think I'm not fully sure if it's 256 or decimal, but there's a limit, and it has to be able to be converted into a number. So you cannot say Pablo, Andre, Oscar, and whatever. They have to be numbers. Okay.
One thing about the number is, Oscar will know more about it, but it's some kind of digital sensors. For example, I know about gyroscope, accelerometers, and barometers. They have already an IC address embedded, like coded on the programs, on the internal programs. So when you want to connect 2 sensors that are exactly the same, you will have collision address problem, and you will not be able to talk with both at the same time.
Yeah.
Only you change your address.
Yeah. So, for example, one example that I know that I'm quite familiar with is Seed Studio has this temperature sensor based on what we call the SHT31. This guy. And let's see, do we have more pictures? So on the device, you see here, this is I2C sensor, and it says I2C address 0x, so 44. So it means that when you talk with this sensor, the address is going to be 44, and you just initialize wire and you request data from the number 44. And some of them just have this configuration, and it's not possible to change it. And some of them, for example, the manufacturer if you buy them, some of them, they will send them alternatively. So they will be sending, for example, 2 of them, one with the 43 and one with 44. And the idea is that the device, at least, you have 2 possibilities. So that if you want to connect it to the same chip or the same I2C bus, and you have don't have this problem that Eduardo was mentioning. Some other chips have a jumper that tell the chip inside if you want to select the address that is the 43 or the 44. And you have a little bit of solder that you open or close, and basically tells the chip the address. You are able to choose the address between 2 options, so that if you want to put 2 or more, you are able at least to put them in the same circuit, and don't have to modify anything. Okay. Now, another example, if you want to send data, so in this example, we were doing a master as receiver. We can do, for example, master as sender, and they can, of course, they can both live at the same time, and the master can send or receive the same as the slave. So in this case, we're going to see master as sender. So we start the same way. The master doesn't need an address, and we're going to begin the transmission, and we're going to send to device number 8, and we're going to write whatever we want, and we end the transmission. On the other side, instead of it was the same, right? Instead of on request, so instead of when the master requests data from us, we're going to do on receive. So when I receive data, what do I do with that data? So what I do is a function called receive event, and we're going to print that data in serial, and we're going to show it in our computer. So
Óscar, I have a question. On the first example with the master as a receiver, you are requesting data and asking for a certain amount of bytes before actually receiving the data. So do you actually have to know how much data you're going to get back before requesting it?
Yeah, exactly.
That's always the case. There's no way to request data without knowing how much it's going to come back.
I have to check. I think probably there's a way of where request from.
I mean, I guess you can ask for a lot of data and then, you don't use it all. But...
yeah, I was going to say, you can probably say, send me like 20 bits and then read just the start.
I'm not fully sure, but let's see, in master reader, request from. So address, quantity, stop, the number of bytes to request, Boolean, true will send a stop message after the request, releasing the bus. Okay.
Well, you probably can just make a long message and then specify a character which you cut.
I'm not fully sure. The way that I've worked with it, when I was working in it, I knew that, for example, I had a sensor reading that was, I don't know, maximum up to 100. That is representable with, a byte. Because with a byte, I can represent up to 256. So I just said, okay, I'm gonna request always 8 bits or a byte. And I know that the data that can come from the sensor is gonna always fit in a word that is of length of a byte. But for sure that these things have, I think, but I don't know at the moment if it's just but if you can just request an unlimited quantity.
Okay, don't worry.
Oscar.
And then
Or you can always filter the data afterwards, right? I mean, like in the end, like you can tell the sensor or whatever you're using, mark this as with an L letter before you give me the data, and then you just filter all the L's. I think I'm currently using a sensor, and that's the way I use it, and it's using the wire H.
Okay. And what you use that L for what again?
It's a RGB sensor, and I use the wire.h library. So like it's like it's on all the time. So when it receives something, I'll just like, I want the red value, and then I just filter all the R's. So, I mean, like, it's not that I request a specific amount of like time or data. It's just that after that, all the data, I just filter it.
Okay. Okay, so it would be interesting if you wanted later to share how you do it. Just keep in mind that even if you use, like you're saying, even if you're using a more generic protocol like I2C or something, there are inner parts of the protocol that you can tweak. For example, as he's doing, or you will have to do. You will send the data in ways that you can make your own protocol inside, and that is very likely going to make things more efficient in terms of transmitting data. It's gonna cost less data loss. It's gonna take less time and things like that. You had a question, Marco, I think.
Well, it was more of a general kind of question. Like, are all the network protocols having master and slaves, or there's more like I don't know, ethical ones, or even like dealer and junkie? I don't know.
Equalitarian.
Equalitarian protocols. No, there are some that can be that are not like this, but generally this idea of master slave is replicated almost everywhere, because at the end, just the network topology will have like something that is the brain and something that is the limbs, let's say, and that can be a sensor or an actuator. And we don't have to humanize this. They are just chips.
Well, I tend to
they're not gonna feel bad and rebel against us.
Marco, you should have started with, I want to use Linux and have a democratic protocol.
Exactly. Yeah. Oh well. Okay. You're gonna like. So what happens when this wire function, this wire library doesn't fit in your in your brain, because you are using, for example, an AT-Tiny. So there's one library called TinyWire, and it has two versions: TinyWire M for master and TinyWire S for slave. So these two libraries. So in Wired you have both of them implemented for master and receiver or slave. But in this one, since what you want to do is optimize the space, you separate both sides. And if you have, so this is even less inclusive. If you have a chip that is going to be a slave, it's going to be a slave and it cannot change, because the only library that is going to learn in its life is the slave one. And if you want to change it, you have to flash it again, and you are going to be a dictator and not flash it. So it's going to be a slave for all its life. So TinyWire S, it's a way of implementing I2C for AT-Tiny. And basically, well, here we have an example for using TinyWire as for I2C in AT-Tiny. So here we set up the address. There is no an implementation of I2C in many AT-Tinys per se. So they use what we call a TWI, or a two-wire interface, which is another, like the same way as we talked about software serial for serial communication. This is the same way. So they are using lines to transmit I2C data in a protocol called TWI, but they are using not dedicated lines for I2C. They are just what they call two-wire interface. And this is what you're seeing here. And this is where you set, for example, the buffer size. We set the whole things, the sensors and whatever. And we use this tiny wire the same way as we would use wire in a bigger chip. So we begin, in this case, we are talking as a slave. So we begin with the address, and we set up a callback that we will do something when we receive a request. And on that request, what we're going to do is send the data on, let's say, in an array. The thing is that you can do this if you have a lot of data that doesn't fit into the words that you are sending. You can always send it in chunks and keep track of the chunks that you have already sent with, let's say, an index position, and send the what we call the sensor readings or whatever you want to send, by using like an array in that, and keeping track of the index of that array that you have already sent. So it might be that the data doesn't fit in one package, let's say, and you can request data many times, and that data that you send, until the package is complete, you keep track of what you've sent using an additional variable. And in this case, what we are doing, and this is, for example, something you can implement if you're using sensors on these things, is that we are going to keep track of the time. We are going to check if the last time we read is, so if enough time has passed since the last reading. In this case, I think it's 550 milliseconds. So basically, with this instruction, we are checking that we are reading and sending data always at the same, sorry, we are reading only at a certain speed. We read the sensor, we do some conversions as we want, and then we put that reading, in this case, we're reading air pressure, into the array of data that we will use for sending it to I2C. And then we just keep going over and over. Then when we receive a request, and the data, the last data that we have recorded, and that is in this array called I2C regs, will be sent in sequence. And if they only request for 8 bits, then we will only send the first part, and then when they request again, we will send the second part. And this, in this way, you keep reading, and whenever you get a call, let's say, or you get a request, you send the data, the latest data that you read. Okay, there's no buffering here. There's no way of storing unless that you keep variables in your stack, or that you have an external, for example, SD card or this type of thing. Is this more or less clear?
I have another question, Oscar. With the I2C, like we're discussing, like in other code examples, like the slave addresses are like hard coded, right? Like say like 8 or whatever, right? Like a number. Is there any way, like, or how do you go about doing something where you don't know the addresses beforehand? Like for like I'm always thinking about the final project, and I have like different modules that could be like connected or disconnected, and none of the like the idea would be to be modular, right? So any module could be any address at a certain point. So like, is there any way like we can connect advice to the bus request for like a new address or something, and then do the wire begin, or do we have to always do wire begin in the setup?
So they need to have independent addresses on the setup. But what you can do is on the master side is have make a scan of the addresses that are connected. And once you know that those of them, you can request to each of the addresses what they are. Basically, imagine that you have a device or you have a pack, and each of them have different addresses, and that's by definition that it has to be that way. But you don't know which ones are connected. You can again do a sweep and get who are connected in the bus, and I start asking who is who and what do they do. But there is no way of assigning the address afterwards, at least in this protocol.
Okay. So there's no there's no way to run like the wire begin after the setup, right?
No. There's no.
Okay.
That's our restriction. Yeah. So what else? If you want to use this in Python, there's one library. For example, you want to use a Raspberry Pi or similar, you can, or for example, ESP32 with MicroPython or these things. I don't know if SMBus is implemented in MicroPython, but in a Raspberry Pi it is. And this is an implementation for using I2C in Python itself. So again, the same. You have two buses actually in the Raspberry Pi, I think, 0 and 1. You pick one of them, you define the address, and you define how big the packet is going to be, and you request data like this. So you, with the bus object, you say read I2C block data from the address, and I don't ask me what is it, 0 and 1, I don't remember. And then that measure, you put it in your value. And remember that you have to sometimes do these weird operations of bit shifting and these type of things, because not always the data is going to fit in one word. So you can just send 4 bytes or 1 byte or 4 bits or whatever. And in this case, you have to do these things so that the data that you receive, you put it accordingly into the value that you are aiming to read. And the same for sender. Instead of read I2C block, you write I2C block data with an address and the values that you want to send. There is another one.
Wait, if we are using this kind of Python implementations, we don't have to use it in both sides. We can use the C1 for example, the IT Tiny, and the Python because we have a Raspberry Pi.
Exactly.
So,
yeah.
so it is the same protocol. It can talk to each other.
Exactly. Yeah. So the protocol is somehow agnostic of the device it's implemented in, and the idea is that you can make a Raspberry Pi talk with an AT Tiny, with an Arduino, with whomever you want. Yeah, the protocol is totally independent. It's the same way of that my MacBook is talking via Wi-Fi to your I don't know, MSID computer, and the communication is just the channel is just a channel. Just one reference, and I think this is a little sad, especially for this week. Not sad, like we're gonna cry, but there's a library in C++ called WiringPy, made by one guy, fully open source, super nice implementation. That this guy that quit doing it because there were companies taking the libraries and closing them. He was releasing the libraries with, I think, GPL licenses, so open source licenses, and there were companies taking it and modifying it because it was like very good implementation, closed sourcing it without giving any attribution or keeping the licensing as it was. And he had to go into a lot of troubles with, let's say, like people suing him, prosecution, whatever. So he stopped doing it, and now the library is no longer maintained because yeah, the guy just stopped. Just got tired of the thing. Maybe one day. I think I haven't checked the website in a while, but but probably he came back. I don't know. But last year he was very tired. And here, just so you see, if you install the I2C library, this is C++, not Python, and it's really well done. And it's very well documented as well. So check the website and have a look at it if you want. It's C++, but for more complex architectures, not like Arduino or this. Okay. And last thing, okay, so we went from asynchronous, serial, we went to I2C, synchronous, and now we're going to talk about SPI. SPI is synchronous protocol, so there's a clock, you already know that, but is serial interface. You have seen this one already because it's the one that you use on the AT-Tinies or the programmers for programming when you did the programmer, for those who did it in the first week, the Niels Fab ISP. And it's a protocol that, again, sorry, is a little bit unethical master-slave thing, but has 6 wires. 2 for power, VCC and ground, 1 of them for clock again, and 2 for communication. And this is a little bit like RxTX, but more like a little bit more dedicated and in synchronous way. So MISO is not a SUP, is master in, slave out, and MOSI is master out, slave in. Okay, so these pins have to be connected. So you have to keep in mind who is who from each side. But it's not like RxTX that they have to be connected to opposite sides. So basically, you will have a wire that goes from the master to the slave, and the communication will be done from one side to the other in the MOSI line, and MISO or the communication from the slave to the other or to the master in the other way. And of course, the clock is shared and is kept by the master. Only the master can generate the signal, as we know, and master and there SPI is a protocol that, as I2C, can have several devices connected to the same bus, but there are no addresses in here. So for you to select who is not hard-coded addresses like in the same way, so for you to select the slave, you have a line that is called SS, unfortunately, it's called slave select. And this way you pick which of the slaves you want to talk to and wipe with the thing. So in the case of the 5SP, you already know this, and we can probably wrap up a little bit what have we been talking about wire communication, what is happening when we program an AT-Tiny using a Fab ISP. So we have the target Fab ISP, sorry, the target AT-Tiny, which has a 6-pin connector. In those 6 pins are VCC, reset, MISO, MOSI, SDK, and ground. Then we have the programmer, that on one side reads serial for communication, and on the other side sends SPI. And on the other side, we have the serial port and here you could have, for example, either an FTDI chip or a USB or a chip that talks to USB. And here you have your computer. So in the same chain, you have different things going on. Bridges, we call, for example, the ISP will be, in this case, will be a bridge between the data that comes from your computer via serial and goes to your AT-Tiny at the end via SPI. Okay, and you have done already this. It's nothing like it's like super complicated.
And it's badly connected, the transmission and receiver on the left.
It is groundly connected, yeah. But this image is, I don't know from where. Probably I took it, yeah, from Admel. So you, if they don't know how to make these diagrams, how are they going to make microcontrollers? Okay. Okay. So SPI, why is it used for this, for flashing these things? First, because it's reliable, and second, because it's very fast. So if you want to send data, for example, to code onto the flash memory, or read data from an SD card, or these type of things, even if it's a serial communication protocol, but since it's synchronous, and that is an important thing, you have very high speeds of communication. And for example, you can have a very reliable and fast communication, and for example, from reading data to an SD card. And if you use an SD card reader, for example, you will have in your board, you will see SPI for sure. Okay. So important things here that the master can talk to multiple slaves, but only one at a time. The master is the only one that can drive the slave line and low to select one slave, and that's pretty much it. But going to a practical thing, important is the library for SPI is nothing weird. It's called SPI. So include SPI. SPI.begin. Before that, you put this line, digital write serial slave select, sorry, to high, because the slave select line, if it's low, it means that we're going to select one slave. If it's high, we just keep it, we don't select anyone. And here, we're going to send the data one character by one character by enabling slave select first, turning it to low. And when we finish the communication, we enable, we put it back to high. And if you want to implement SPI or use it on an Arduino, check this. But my global advice is that don't try to be a superhero by implementing these things off the shelf. If you have sensors that talk I2C or these type of things, the best thing that you can do is go to the go and check if there are libraries already that are done by others. For example, I2C SHT31. So if I want to read an SHT31 sensor, I won't implement it by myself because there will be a lot of little details in that. But I will go, for example, to Adafruit. I will just do this check. And here you go, you have a library for Arduino made by Adafruit that you can just use to read the temperature and humidity sensor. And you will have a lot of examples, well, at least one that works. And here you see that you include the same library we were talking about, wire. You include the library. You declare the object, begin. You remember we said that the address was 44. And you see that there's like an alternate I2C address for some other pieces, which is 45. We try to find it, and then we just say SHT31 read temperature, SHT31 read humidity, and that's it. You don't have to implement and start trying to understand how the bits were sent and one thing and another. So look for libraries first and try to understand. If you have a very custom setup, then you implement your own. But if not, if you're using something that is already a little bit common or somehow mainstream, try to look for libraries for SparkFun, for Adafruit, Arduino, and this type of thing. And if you make something yourself, contribute it back and make a tutorial, and other people will be happy. What else? As well, that's it. That's it for wire communication. Do you have any questions? Before we take a break.
Is there any reasons to prefer SPI to I2C or
speed and reliability?
And in which case, do you need speed? Sorry? For example, sensors, I guess, are pretty slow. And in which case would you need SPI? Like how fast or what
like
kind of device?
As fast as, for example, you want to read gigabytes of data from an SD card in very short time, or you want to flash code into a microcontroller, or this type of thing. Normally, sensors work with I2C because we are talking about milliseconds range of data transmission. But when we talk about SPI, we're talking more about nanoseconds or microseconds range of data transmission.
And SPI is more sensible to the wire length than I2C and the wire quality because you're transmitting much bigger amount of data. So actually, if the wire is basically has a lot of resistance, you might lose some packets. And if you're transmitting a lot, so that's why for this kind of protocols, you care a lot about the wire quality. If you shield it, it has gold connectors, etc.
Yeah, I just want to mention something because this is a very important point. I2C normally is limited to around 20-30 centimeters cable. Longer than that, you can experience data loss. And the important thing here is that you already know that we are transmitting data by changing voltage levels. And basically, we're saying either we have 0 or 5 volts. So I just want to make that point a little clearer and imagine that we have, well, that was really straight. These two lines, this is even better.
Oscar, so, I want to be like you. I cannot make a straight line.
The bottom one is perfect.
The bottom one is really good. But I think that Zoom has some sort of feel-good feature that makes the lines somehow straight. Anyway, so wow, really nailing it today. So we have 5 volts in here. So this is our voltage. And this is a wire. This is just copper or aluminum or something metal that has very little resistance. And the length that we have in here and the voltage that we have on the other side will depend on, the voltage that we have on the other side will depend on the length of the cable. And why is this? Because even if we have a very little resistance on the cable, you can say, for example, I have 20 ohms per meter, means that I have like a cable of 1 meter is equivalent to 20 ohms in resistance. That means that you have a little bit of voltage decay along the line. So the way you can see this is if you imagine that you have, let's say that example, that case, 20 ohms per meter, and this is equal 1 meter. It means that it's like if we had little resistors in here distributed along the line, and little by little, the voltage that we have is smaller and smaller. So for example, imagine that we end up with a voltage of 3 here. So we will have something like this. Like that, more or less, okay? And at some point here, probably, this goes below a threshold that is no longer valid for us to assess the communication. And imagine that our communication only works down to 3.7. So I consider high to a value that is over 3.7 and low, a value that is lower than 1.3. I'm making that up, okay? So if a signal is oscillating in this range, it's not going to be perfect, but it's oscillating here, I consider it to be high, 1. And if it's oscillating here, I consider it to be low. But if my line is too long, so that this little resistance accumulates, and at the end, when I send a 1, I am getting a voltage that sometimes goes a little bit like this. All of a sudden, I enter in an unknown state that I don't know if it's high or low, and then my communication fails. Okay, so that's why it's important, and we said that wire communication is meant for distances that are device within the device limit, or let's say within a table or desktop limit. If you want, of course, you can use USB cables, and you have seen them probably, or other more complex things like Ethernet and these type of things. That's a total different story. But Ethernet USB cables, for example, that have that can be 10-meter USB cable. But what you do is that in the USB cable, you put a little amplifier that is powered from the plug, and you have 5 volts in here, and this is in charge of injecting voltage here, keeping the voltage, the decay, instead of doing this, doing something like this. Okay, but you need this sort of amplification, and if you don't have this amplification, at the end you will end up with this problem, and you will lose data. Okay.
You also
so
feed a higher voltage if you know how long the cable is going to be.
I don't know exactly how that works.
But Benjamin, the problem of that is like you need to design like the amplification for your system, and that's something that is in the industry is not really reliable, because you need to customize every time. So what you do is amplify or change the wire quality. For example, if you see your 6-pin connector of the Arduino and the things you use, they're all gold. Actually, it's not just yellow; they are gold to actually kind of reduce the resistance of the connector that you use, so you get less amount of errors as possible.
Okay.
But once you get to like 10 meters or something like that, isn't it better to just use like wireless communication?
No, not always. That's something that depends really on what you're doing. For example, if you are working with heavy industry equipment, you don't want to use a wireless communication, because you are dependent on big machinery that maybe weighs tons, and is managing like just the cost of breaking or stopping the machine because one loses that ticket could be around like 10,000 euros, like on 5 minutes stop. And not only that, but also on safety. Like if the machine that usually in industry, you have big machines that they are moving along all the industry, and they are moving on their own, you don't want to have this kind of problem. So you use like protocols like for example, the USB is the AirAS232, and for example, for industry is AirAS485. That one, for example, allows like more than kilometers length with only 2 cables. And what you do actually is you reduce the amount of cables, but what you do is you use really good cables that are triple shielding to avoid like problems like interference in the industry, etc.
That is, you remember the class we did 2-3 weeks ago about output devices, where we talked about where is this? My whiteboard. I lost it on. So here. So the shielded.
We see the whiteboard.
Yeah. What I don't see here. Okay. So what Edu is saying is that in cables, wow, this is straight again. Like, so you know that when you have a magnetic field or currents going into wires, you generate magnetic fields, and when you have magnetic fields around them or electromagnetic things like Wi-Fi, communications, etc., things can get in voltages can get induced into cables, That's how motor works in like very simple level, like induction and these things. And if you're transmitting data over a line, and there are things that can affect the voltage levels in your lines from the exterior, that's what Edu means by interference. And what you do in general is that you put a shielding around it, so that you can protect that magnetic interference from going into the wire. And that's, for example, like audio cables or Ethernet cables, Canon cables.
Just the TV table, the TV antenna cable is a big coaxial one that is just like that.
And so you see it looks like this type of thing. It has like
it's your whiteboard.
or sorry. Thank you. So it looks like this type of thing. Okay, so either with like tin foil around it or some sort of mesh in it. You also have like the external ground or external like inductance correction and this type of thing.
Yes, and those ones you can find them like in 3 shielded layers, single shielded for each one of the cables after a second shield and a third outer shield. Actually, that's just if you're curious about this, just look for internet under the sea like cables, and you have some videos on YouTube that they actually start opening the cable, and you can see how many layers of shielding they have. Like for wastinet, one for like sea animals, for rats, for like interference, they have, because they are basically going through the whole Atlantic or the whole Pacific. So actually you have to keep really long distance data. And also for the wireless communication, is something that nobody realizes, but it's really weird that you don't lose a connection at least once a day in any kind of protocol or any kind of radio. You can really notice the amount of interference that we have in the cities and everywhere. And even like from the police, like I know because I have a radio frequency scanner, and you can't believe how many times the police goes and jams the frequency just with the car to erase kind of like bomb attacks and like activating big things. And it's something that they do kind of daily, everywhere. And that's in Wi-Fi, for example, sometimes you notice that it goes slightly slow. That might be probably because the connection on the server is going slow, or just because suddenly like something got jammed and you lose the frequency connection for just 1 millisecond and it's reconnecting back. But that happens lots of times in all kind of radio frequency and wireless communications. And there is ways to solve it, so actually we don't feel it in the way how we interact with the devices, but it's happening, and you cannot have this kind of possibility of error and mistake in an industrial system.
Well, before going to the break, and I just leave you alone, I don't know, Edu, if you're going to talk about this, but if you want to do some hacking or this type of things, you can read a little bit about SDR. So imagine the antennas that Edu is going to show you are defined by the hardware configuration, so the length of the wire that is that you put the piece of metal, let's say. But there are antennas that you can define by software. And for example, in a single piece of hardware, you can have antennas that are able to listen to many things. And this can be used, for example, to read data from, I don't know, communications of the military, the physics or scientist community, communications from the police and stuff. Of course, it doesn't mean that you are able to eavesdrop and listen to them, but at least you can receive them with just a single device. And if you want, there's a very interesting project called GNU Radio that is like an interface that helps you use an SDR and analyze these frequencies. And there are a couple of videos in YouTube of people just putting this, for example, in Australia and listening to communications of the marine observatories or tests from the military or this type of things. and it's really, really cool. So if you want, for example, to know if the police is jamming or the communication and the things, you can use one of these as well, and use with GNU Radio. And that's it. Let's take a break.
I just had one question about the optic fiber. How does the optic fiber works? Since I don't know, for me it's like a plastic fiber. So does it transmit electricity too?
No, it's light. That is really a beautiful concept. We will talk about the actual protocol on Tuesday, I think, with Guillem. But optic fiber basically is, let me bring this resume share whiteboard here. Okay. So you know that light, when changes, do you see my whiteboard?
Yes.
Yes.
So imagine that you have a bucket of water, and you have a laser. So you know that when the light goes in, it's gonna go and change direction, right? And this angle of that is not gonna go straight, let's say, as it should. In principle, it's gonna change and get diverted because it's changing the density of the means in which the light is transferring, right? So, and that happens, you know that when you look into a bucket, it looks like the things inside the bucket are a little bit crooked, right? And that's only because the light has this effect of like partial reflection, in which the light actually gets reflected somehow and partially diverted. So optical fiber uses the principle.
That's why it's difficult to fish with a stick, because you get to know how the reflection, the visual reflection.
So two things in here. One interesting one is that when you this oasis thing in the desert, you know that when air is hot, it changes temperature. Sorry, when air is hot, it changes density. So if you are in the desert and you are really hot with your cup, and you think you're seeing water, and you see that we could think that the desert has so this is a temperature equal, I don't know, 50, and the air is a temperature equal 25, I don't know. So there's what we call a gradient of temperature, right? So the air in here is like 40, 35, 30, 27, whatever, okay? So the temperature is going down as you go up, because they're just as simple as the ground is, the sand is hot and the air is not, okay? Because the sun is hitting the sand and is heating it up. So when you look at the ground, you would look and see this, but since there's a difference in temperature and then therefore there's a difference in density, so as you go up, the density is going. So as you go up, density is going up. Means that little by little, what you see is getting changed by direction, and you start seeing something like little by little like this. And at the end, what you see is the reflection of the sky or whatever else is in front, because the light is doing this trajectory. And you happen to see that there's like this water effect in there, but there's nothing, there's no water, and this is like hallucinations that people have in the desert. It's because of that. It's because the light that you actually see, you're not actually looking at the sun. The light is going and making this thing, and you're seeing whatever else is in the background. That could be just the more sand, or it could be a mountain, or it could be palm trees, or it could be the sky. And you have this thing that you all have seen in the roads and stuff when they are very hot, that it looks like there's water, but then you go close and there's nothing, right? And optical fiber somehow uses the same principle. And optical fiber is just a cable a piece of material, I don't know if it's plastic or resin or something, that has a different gradient density inside. So the idea is that you have a core that has one density, then another one that has a little bit more of density, then another one. So you have different layers around it, and the density is changing when you go out of the core. So if you were going to send a beam of light inside this cable, what you would do, so the light could be like going in any direction, and if it was like straight, it was perfect, right? But the cable could be bent. So the idea is that this gradient is done so that when the light goes like this, little by little, it comes back and it stays more or less always in the center because of this idea of light being able to change direction because of the density changes on the means that is transmitted with. So if you have things like this, then the light is reflecting and coming back to the center and always getting transmitted across the whole line. And I'm not an expert on this, but the way that you manage light in the switchers, let's say, and this is a technology that started being used recently, and that's why we have a lot of a bigger spread of optical fiber in the cities. Is called GPON. Is gigabit capable passive optical network, and is basically the technology that does the switching to be able to send these little pulses of light of information without losing data. And those are the black boxes that you see in the streets. In the streets, no, normally in the rooftops, that the company gets in there with a big optical fiber cable, and then different optical fiber go down to your house or whatever, and that's what you receive. So if you are interested, you can read a little bit more about this, and there are video tutorials, video explanations of this on YouTube about how this technology works. Oh, sorry, you don't see my screen anymore. You see still you still see the whiteboard. So it goes like this: GPON, and you can look for it in Wikipedia, and it's like how this is. And you can use, if you want, this video is very good explanations of the GPON technology. Okay, but optical fiber is just like a fiber with different layers that have different densities, so that the light is kept in the cable and doesn't go out, just using this diffraction phenomena in light. Is diffraction or refraction? Does that answer your question? I always confuse them.
Refraction.
Yeah, I think you don't know. Yeah, I'll investigate a little bit.
Refraction, right?
Diffraction is when the angle changes inside the material, and refraction is the bouncing, no?
Refraction is when density changes and it changes the light.
Yes.
So this is a visual thing. So you have this beam of light, changes and changes again, because you have difference in density, and that's what happens in optical fiber, but in a very small scale, to always keep the light beam inside of the cable. Which for me is an amazing invention. Like, I mean, you cannot be smarter than that. You're like top level.
But is it just so it can travel long distances, and it doesn't have anything to do with actual like blinking to transmit data?
Yeah, of course, you are sending data with light.
Yeah, but as in like the making it wave, is that for the transcoding of the data, or is it just so it can
Benjamin,
be sent over long distances?
you remember like maybe the documentaries of the Second World War when they communicate with boats with lights opening and closing? It's the same. Like they basically send the pulses by switching on and off.
Yeah, but it's got nothing to do with the wave. The wave is literally just to send it long distances, like
The
AC
wave,
with electricity.
Exactly, it's just the bouncing back of the light, so it doesn't. You don't have like a light dispersion, so it doesn't get out of the
cable.
Of the cable, exactly.
Cool.
Of the fiber.
So let's say you have the same amount of intensity at the start and at the end of the cable.
Mm. Exactly.
Genius.
Okay. Look, very creative things of showing this. Okay. Break. Yeah. See you when? Well, you decide. Or you guys decide when you come.
10 minutes. And I'm sorry, I want to try. Okay, my God.
You have to be
You got 10 minutes. 10 minutes to train.
How you do it? Yay!
Wow! That's a fake one, man.
That was cheating.
Oh my God, how you do it? I just want to try.
You need to get the same mouse as him. You saw him earlier on the system report, which one to get.
Who is the architect here again?
Daphne, I'm gonna kick you out of this meeting.
Oh, see you later, guys.
Oh my God. Bye.
Okay.
Yes. So thank you, Óscar, for your nice overview on the serial communication and like communication protocols for networks.
You don't have to say that on the recording.
So we're gonna go on to OTA communication. What is OTA communication? It's over-the-air communication. Over the years, we have learned how to communicate data, audio, different kind of information through the air. So that means don't have a wired connection or physical connection between different elements to transmit information. For this is a clear example that's really basic. So the old Navy transmission that they use flags to communicate. So they have different flags and types to communicate and send signals, so they can actually have communication between the boats. To learn the difference of OTA communication, we have to go a little bit onto the basics of physics. And every object emits some frequencies. That means us as humans, as we have material, we have atoms, we have protons, we have electrons, we transmit what's called radiance. And not everything transmitting the same frequency. Frequency is the amount of information or vibration of the particles that you are emitting on time. So what's what we call the radio frequency spectrum. We can define radio frequency of the vibration of the electromagnetic vibration of particles through the air or through materials. So you can see that the Earth field actually emits also radio frequencies. And actually, if you go onto the NASA webpage, they have what's called sound recording of the universe, or how the sound, the space sounds. The sound, us as human or ears can only listen to audio air vibrations. But
it's super creepy as well.
Yeah, exactly. It's more like that. But that is the translation of the radio frequency vibrations to a frequency that we can, it's a translation. We cannot listen as it as human, but everything emits. We have learned through the years that we can control some kind of frequencies and emit through them. So you have, first we need to define what kind of frequency we want to emit with and what kind of information we want to emit in that frequency, because not all the frequencies are good for everything. You need to choose wisely which frequencies you are using for the kind of package of information that you want to send through. So for example, here you can see that the AC power actually transmits also by vibrating electricity, that alternating voltage through the wire lines. But AM does the same by vibration, electromagnetic fields through the air and through the different materials. we can see that also satellites work like that. So one of the first things that you want to choose is what kind of frequencies you are emitting. Of course, the frequency band is going to tell you not only the range, it means how far you can reach, but the amount of data you can transmit. So we consider like this is the commonly used radio frequency emitting spectrums that we use, like the high frequency emitting, that is 300 gigahertz to 3 kilohertz, and even some megahertz. Megahertz, for example, will be the AM radio. For example, lower to go on the frequency spectrum, let's say farther you can reach. And this is because of the physical properties of the material absorbance. Different materials absorb electrical wavelengths at different ranges. For example, if you emit in VHF, the radio frequency signals that you are emitting are being bounced back by the ionosphere of the Earth. So that means the radio is not getting out of the Earth's atmosphere. So you are working with what Óscar was explaining about refraction, that is actually using the ionosphere as actually a big mirror that is covering the whole Earth, so you can reach longer points of the Earth. And actually that's how the radio frequencies are used through long distance. Because by using a low frequency wavelength, you can use the ionosphere as a mirror to reflect back in another point. Because scientifically admitted is that the Earth is not flat, it's more or less like the shape of a potato. And you can actually communicate to other points of view that you don't have in what is called loss, that is line of sight, not different line of sight. And actually a line of sight, more or less on a human scale, a human can only see more or less a maximum on a flat terrain, a maximum between 2.7 to 4 kilometers length, as considering that the standard human size is around 1.75 meters. So if you are shorter, maybe you don't see 2.7 kilometers, maybe you only see 2. We have to talk about material absorbance. Different materials, because they have different densities, actually absorb the vibration frequencies in different ways. That means depends on the wavelength that you use, you are able to transmit through the materials or not through the materials. For example, I don't know, but maybe you have some like annoying neighborhoods that they love to play like some trap music. Trap has really big sound bass and low frequency sound. The wavelength of sound for bass is really what is a low frequency spectrum. That means the wavelength doesn't match actually the, I'm going to draw in a whiteboard. Okay, clear all drawing. So for example, low frequency has a wider wavelength like this. Higher frequency is shorter. So that means when you bounce an object, if the object has a material density that the frequency matches the wavelength completely, the whole cycle of the frequency, that part, oh my God, my drawings are much worse than yours, Óscar. So if the wall actually can fit a whole frequency inside the material, not only by the material thickness, but also on the material density, that wavelength is going to be absorbed by the material. On the other hand, if you have a bigger frequency, to be able to actually isolate and absorb that frequency, you will need a wall of this size. That's why some kind of frequencies, they translate better over the air and over the distance, not only based on the distance itself, but also on the material properties and the densities and the material thickness that you are transmitting through. Can I go back to my screen? Okay. So for that, we use different kind of radios, frequencies and radios spectrums. Depends on where we want to transmit, how far we want to transmit, and what is the amount of data we want to transmit. For example, something that is easy for you to understand is the 3G, 4G communication and the 5G. You have noticed in your phone that 3G, that now we almost never use, is slower than 4G, no? Like we are going we can download full HD videos in just a couple seconds. Actually, that's because we are changing from the frequencies, 3 gigahertz, 4 gigahertz, 5 gigahertz. So higher do you go on the frequency, you can fit more amount of data in less amount of space, because the frequency wavelength is denser than the 3G. That, on the other point,
wasn't it about generation, the second generation, third generation, fourth generation, fifth generation, or it's actually about the frequency of the gigahertz?
They are also changing frequencies.
But yeah, at the bottom, like 5G is 10 gigahertz. It's not 5, so I guess it's the generation.
Yeah, but they depends on the country. It's a mix of standards of software, communication protocols, and frequencies. For example, right now, a few months ago, they changed all the TV spectrum, and you have to resynchronize your channels, because actually they have left some space of the frequency band of the digital TV to be used for the 5G that before was not being used for by the 4G. So actually they are going higher in the frequency spectrum because they can transmit more amount of data. So the difference between, well, actually it's here, like 700, 200 to 10 gigahertz. So actually when you go to 5G, you are transmitting more amount of packets per time on the frequency. But at the same time, you are reducing the range. Why? Because the frequency is higher the frequency, shorter you can get in range, and also has worse material penetration. For example, you have noticed that when you go inside a building, the first thing you lose is 4G. You go deeper in the building, let's say to the subway, you may not have 4G, but you have 3G, because the signal wavelength doesn't travel well through, let's say, the soil. And after you lose 3G, what you still have, it's difficult right now to have lose the network connection of the phone on the phone. Why? Because actually we are using below 600 megahertz. Usually it's around 400 to 300 megahertz. So actually that the wavelength and the data transmission is less amount of data that we can transmit, because it's just sound translated to radio frequency signals. So you have less amount of data that you have to transmit by frequency. So depends on and actually that's why we cannot see through the walls, because with light is actually a vibration also, vibration of photons. And basically, if the photons will able to travel through the materials, depends on the material properties, the absorbance, reflection, and density. That's why we can see through the walls, through the glass, but we cannot see through the bricks. This is a little talk about frequencies. Let's go a little deep into antennas. So what I'm going to have just an open question on antennas. Chat cleaning. So what do you know about antennas? What do you think an antenna is? Open question.
Something antenna is something that
radio transmission
broadcasts or receives the transmission.
It creates waves.
Creates or absorbs waves. That's actually much closer. Benjamin, your definition is much closer. So actually, what we commonly know as an antenna is a piece of metal that matches the frequency, physically, the physical frequency of the wavelength spectrum that we are reaching or transmitting. That means the same as we have the walls, let's clear this, clear all drawing. We have the frequency going up. If you want to have an antenna that matches the frequency, the physical shape of the antenna needs to match this frequency spectrum. So actually it's a piece of material that absorbs a complete one cycle wavelength. So that's an antenna by itself. So for example, us are humans, we are the same material and more or less the same mass and density, depends on the person. But basically when Benjamin is, for example, next to Óscar, is emitting some frequencies, and actually Óscar is receiving the same frequencies. They are, let's say, one could be the antenna of the other one. What we do, we have learned that we can match different kind of frequencies and spectrums, and we usually use between 300 megahertz to 30 megahertz to like 100 gigahertz. We have learned that metal that has a lot of electric conductivity, we can match different kind of frequencies. So let's close this screen again. So we have different types of antennas, and each antenna has always what is called the active element. The active element is the sensing element. So this little antenna is going to match one cycle of the frequency. And we have a big secondary part of the antenna that obviously one is the connector, in this case for the electrical circuit, and one that is the coaxial cable or the ground plane, the grounding. So this part is quite important. Why? Because if the wavelength is going, you see my mouse, no? Yes, okay, so the frequency is going inside, you don't want to match more than one wavelength, than one wave of the frequency in the antenna, because that means you are kind of receiving duplicate data in the antenna. So what you want is to isolate and only receive one. And we do that with the ground plane. That usually is a piece of coaxial cable. What is a coaxial cable? As we explained before, is just a shield cable. We call coaxial when we just have two cables. A shielded cable is a piece of cable like this that is protected through a metal mesh. That metal mesh is usually connected to ground, and by connected to ground, we isolate the magnetic interference that this cable is getting. A coaxial cable, just for antennas, coaxial cable is actually what you have on the TVs that you have mostly see when you have assembled a TV or the wire has broken. That is a center cable that is going to be, or is not, or positive, because in this case we are not transmitting electricity. We are receiving electromagnetic fields. And with this little internal core of the cable, we get to accouplate one frequency, one wavelength frequency with this cable, and with the other one, we isolate the rest of the wavelength. So actually, what makes the antenna is the shown part, like the part that is in the air of the antenna. You have seen that this kind of antennas, maybe you probably haven't seen unless you have gone to some radio communication towers, etc., are different designs of antennas. And they have different purposes, and each one amplifies or decreases the range. So depends on what you are transmitting, which direction you are transmitting, you want to choose one type of antenna or another one. For example, this, what is called circular polarized mushroom antenna, are usually encapsulated in some plastic, because these antennas are quite easy to break, because it's usually a really thin piece of cable or metal that is weak enough and has enough like quality of reception. That means the resistivity of this piece is really low, and usually that means that if it's made of gold, has better absorbance than other materials. So depends on the antenna, you will have what is called radiation patterns. That means radiation coverage. So imagine that we have the rule of the three, X, Y, and Z. This antenna will have X, Y is on the screen, and Z. So this antenna can actually receive the wavelength in which direction? Actually, this antenna is meant to receive the wavelength in this direction, because the frequency, the band, needs to accouplate this height, and this height is the height of the frequency band. Of course, the thickness of the antenna also matters, but it's not that important as the length of the frequency band. So actually, when you want to, for example, reach a 3 gigahertz band, this cable needs to be cut physically to the same height, physical height of your frequency band. So what happened, for example, in this direction? Actually, the material that you have here is thinner, so actually it doesn't reach the frequency band. That's why we have other antennas designed that solve this problem, because this is a simple dipole antenna. So depends on the type of antenna that you choose, you can receive data in different zones. For example, you have the standard, like the ones that the antennas that you have in your router, that are just a pole stick. This is a dipole antenna. You actually don't receive data on the top, on the tip. It's impossible. They have a radiation pattern of a donut. And where they get the best range is actually in the perfect center around them. So I have seen a lot of people that usually they have really bad connection to the Wi-Fi and say, okay, I'm going to point my antenna to my phone so I can get better connection. Like if the antenna was transmitting in this direction, but actually it's the opposite. The antenna transmits horizontally. So actually what you want to have is always the antenna parallel to your device. And when you have several antennas, what you want to have is actually mix them and make angles. So you have one donut that is covered by the other donut. So with that, you can have, let's say, a full sphere of radiation for reception and transmission. You have omnidirectional antennas. Omnidirectional antennas, that is also, for example, a dipole, is antennas that can receive omnidirectionally. That means, let's say, in 360 degrees. Of course, they will have some zones that will have more sensitivity than other ones. That is happening with the dipole. So an omnidirectional antenna is transmitting, let's say, 360 in an XY plane and have a little bit of reception or transmittance in the Z. The Z is going to be determined by the physical shape of the antenna. You have directional antennas. Actually, I don't know if you have the plan of directional antenna here. Yes, for example, directional antennas are antennas that in an XY plane, they receive much better in one direction than the other one. Because basically what you are is only listening to one direction. For example, if you cut your ear, what happened? You only hear well with, for example, my right ear. Why we have two ears? So actually we have omnidirectional, more or less omnidirectional sound pattern. So if you look at a human sound wave reception will be more or less a semi-donut that on the back of the head, we don't have really good reception. So actually it happens the same with antennas. And some antennas are designed to listen only in one direction. That could be, and we do this, so actually we can focus and only listen to one particular emitter, or we want to only receive in one direction. For example, the TV antennas, they are really directional antennas. They only see what they have in front and what you're pointing to. And that's why they say, like, I need to call the operator so actually redirects my antenna back. And that's important because you only want to receive the information that is coming from the television tower or the television repeater, not from other sources of frequency that might create interference. So you only want to use to actually the one that is speaking, that is the television antenna. So depends not only on the radiation pattern, we have what is called dBi, that is the gain of the antenna. The dBi is what is called gain antenna. Gain of the antenna is measuring this. It's not decibels, but it's dBi. It's called dBi. Actually, it's the sensitivity of the antenna. Higher the sensitivity, usually get a more flatter radiation pattern or radiation reception. That means you can get farther, but only in a direction. So you are losing direction. So usually, for example, a lot of people change the frequency, the antennas of their modems. So for example, a normal modem antenna is a 3 dBi. So it's good for all round working around. So for example, if you have a really wide space, but it's only one floor, you want to have full coverage on the just one floor building. So in that case, you will change to your antennas to a 9 dBi. So actually you can cover more distance in the XY plane, but less in the vertical. That's why, for example, in a house, most of the houses, most of the people live in flats, and flats has only one floor. And you don't want to broadcast your network to your upper floor neighborhoods, neither the down floor. So that's why a lot of times, just by changing the antenna to a 9 dBi, you are actually not increasing the transmission power. What you are changing is the sensitivity of the antenna, and by so you are elongating, let's say, the field of transmission reception of your antenna, and you are getting a fake feeling that you have increased the range by changing the power. What you are doing is actually not transmitting or receiving in other different zones. The frequency of the antennas, as I stated before, for example, depends on the physical shapes different the frequency. This is a clear example of, for example, this is a 5 gigahertz antenna and this is a 1.2 gigahertz antenna. So also matters a lot which cable of device you are designing and where the antenna needs to be operated for. That's why, for example, in the buildings, on the rooftops, we have big antennas because we don't care. What happens if you put a TV antenna on your phone? If the phones use TV wavelength, yes, you could reach much further length, but the antenna will be so huge that actually you will need a trailer to move your phone. So that's why one of the reasons, because we use higher frequency, not only because of the data transmission, but also because of the hardware digital design, hardware design of the antenna shapes. Let's go a little bit on an overview of the different types of antennas. We have monopoles. Monopoles is a simple coaxial cable. Remember you what the coaxial cable is. So, sorry, yes. So we have the connector for the antenna, and you have the cable that is being shielded, and you cut the shielding and uncover the internal part of the antenna. This is the simple antenna that you can do. Actually, this is not exactly the simple antenna that you can do, but the simple antenna that you can do is this one. I'm gonna have to hover a little bit over because there is not too much information about these antennas. It's just a simple wire antenna. Come on, load. So for example, we could have a simple, this is a coaxial antenna. If you just cut here and solder directly this part of wire here, this is the simplest antenna that you can do. It's just a piece of wire. What you want to have is always a little bit of coaxial shielding. Why? Because usually, for example, this is a radio transmitter. This radio transmitter is also emitting some electromagnetic fields around it. So what is happening is your own device, by the physical shape, for example, regulators, emits a lot of electrical noise. And that electrical noise is not only given through the PCB design, but also on electromagnetic fields around the object. So you always want to have the antenna slightly further away from your receiving and transmitting source, so you don't have interference from your own PCB electronics. So that's why you usually have a little bit of coaxial cable to take away the interference coming out from the electromagnetic fields of your PCBs. We have, so with this one, we're going to explain how to actually calculate the length of the antenna. Actually, the length of the antenna is quite simple. The length of the antenna is the frequency divided by C. So, and you have to, and usually you don't want to fill up a spectrum. Actually, this is something that before I explain that you want to match the frequency, a full wave frequency. In antenna design, because of the material properties, we have reached that if you have a full frequency, actually you don't want to have the full frequency on its own. You don't even want to have half, you want to have 1/4. And actually a rule design is that you want 1/4 of the frequency wavelength. And this is something that I don't know exactly why this 1/4, because it's really like radio physics theory that goes really beyond my knowledge.
I guess it means you have small antennas as well.
Exactly. One of the reasons is to get smaller antennas. For example, I know that most of the devices use 1/4 antennas, but really BFH and UH8 frequencies, they use almost the full wavelength because they want to receive the littlest amount of energy as possible. Because also the amount of energy transmitted is really low, so you want to be as sensible as possible. Theoretically, the ideal is to have, physically in theory, the ideal is to have the full wavelength. But practically, we use half of 1/4 of it.
Edu, but didn't you say that the way the antenna receives a wave is having the same length as the wavelength? So how can you actually receive the wave if you're like less than the wavelength?
Bruno, I don't know how to answer that. I have to be honest. It's something that I know by experience and reading a lot, but I can only recommend the same book that Neil recommended because I'm asking this kind of questions to Neil every year, and he always recommended the same book that is a 600 pages like thesis.
Another Bible.
Okay. Yeah, probably it's like signal processing or something like that they're doing.
Yes.
Right.
I have sincerely no idea. So, for example, for a 5 gigahertz antenna, a 5 gigahertz antenna, it means a 5.8.0000000 exactly tuned antenna, you will want to have a 11.71 millimeters length. What happened, for example, if this was 11.72 millimeters length? That do not will be 5.8000. Maybe it's 5.825. It's slightly tuned, and this is called antenna tuning. And actually, by changing the length of the antenna, you can tune to some specific frequencies. And this is something that yesterday Neil addressed, that some antennas are really what is called fine-tuned. They only receive some certain frequencies because the sensitivity of the material and the thickness of the antenna changes how sensible is this antenna to, let's say, neighborhood frequencies. What is a neighborhood frequency? When we transmit, for example, we want to transmit in 27.075, a neighborhood frequency is 27.065. And actually, a really fine tune that is with usually high gain antenna, this antenna will only listen maybe to 2 or 3 surrounded frequencies. But a broader spectrum antenna is able to listen from the 26 to the 27. By so, it means it can receive a broader spectrum of frequencies that sometimes is something that you want, but because most of the devices are changing all the time between frequencies. But if you are designing your own system and you want to be sure that you only receiving that frequency because you never change and you don't want to reduce the maximum amount of frequency noise, you want to have a well-tuned antenna. So we have what is called also dipole antennas. It's really similar to actually a monopole antenna. What we have is a big metal shielding that is connected to the external coaxial cable. It means ground. And usually this little shielding is half of the receiving part, like in the air part of the antenna. And this actually reduces, again, electrical noise coming up from this small wire that is connected to the PCB. It's a little improvement over this one, and it's quite simple. And it's the kind of antennas that we have all over. It's the classical antenna that you have everywhere. And that's because it improves a little bit without actually having to invest too much money and resources, and you can match it. Actually, this is antenna you have everywhere. We have what is called half dipole. It's a slightly different concept, but it's really similar in the approach. You will have the coaxial cable, and in one zone, you will have the ground shielding, and in the other zone, in completely parallel, you will have the wire antenna. This actually has much better range than this one What happened is actually the size is double. Imagine duplicating your antenna as a T. Some like emitters, like modems and nice routers, have this kind of antenna. They look like a T, actually to improve the range and have better coverage. Actually, the dipole antenna has the most spherical radiation pattern. We have helical antennas. Helical antennas, you have the coaxial cable and you have a big ground plane and the antenna itself is turning. Why we are turning is one completely different thing. But usually you have seen, look at my camera, this kind of antennas, no? Why does the antennas are like that? Just to reduce the hardware space. Because actually this antenna is the same as having this small spring elongated completely. By let's say make them helicoidal, you reduce a little bit the sensitivity and the range, but in benefit you get a really smaller hardware. That is something quite important. So in this case, instead of having just a super long stick that will be difficult to manufacture because you will have a really thin piece of metal that will bend with the air and everything. I don't know why you're laughing. Do you have something in the chat?
Yes.
I don't see the chat. Oh my God, really, Kuko?
It's coming.
You have to go a little bit to the left. Yeah.
So what you want to have is reduce the amount of physical hardware by making the antenna stronger. And usually you want to use a material, for example, something that's plastic that doesn't isolate your antenna to it. Usually more turns, what means more turns?
More length.
More length. And by more length, you augment the sensitivity. So the good point is with antennas, you can have a full length, not a 1/4 frequency antenna in a shorter space. These antennas are really, really directional. That means they have a radiation pattern that they only see in the front of it. And usually these kind of antennas have a cone radiation pattern. They also have some radiation pattern on the back, but we consider them as like useless because they have really bad reception. So usually these ones have a beam of around 60 degrees cone. We have also what is called a patch antenna. Wait. Yes, just for you. Ah, no, mine is back. It's only, it needs 1 or 2 minutes more. You have what is called patch antennas. Patch. No, you lost it. Sorry. You will have patch antennas, and usually this kind of antennas is the one that we don't usually see them because they are embedded in our devices. For example, that will be the antenna of a GPS. This is a GPS, a standard GPS. Most of the GPS, it doesn't matter, use an Arduino, phone, or whatever, they look exactly like this. They have the reception chipset, the motherboard, and they have a big ceramic plate that has a metal cover. These antennas, why do you think they are designed like this?
Because they are flat, so they are easy to put it in some boards or on other devices.
Any direction.
Exactly, the direction. Where are the GPSs? In the sky.
Yeah.
So except phones, that is something that we move all the time, that they have kind of not exactly this antenna, they have slightly different antennas. They use what is called a patch antenna, that is a super directional antenna. These antennas can only see more or less in a 30-degree angle. And they have a big ceramic plate to actually do what? Is isolate the radiation pattern in other directions. This. So a patch antenna actually isolates with all the ceramic plate that is a dielectric component, all the directional of the back. So actually they only receive in one really straightforward direction. these antennas, as lower we are going, we are augmenting actually the dBi. This is the sensitivity, is the dBi gain. So these antennas, we are actually augmenting the length of the sensitivity with the dBi. We are getting, let's say, longer range, but we are reducing a lot in other directions. So depends on where you want to transmit, you want to choose one antenna or the other one. For example, this is also another patch antenna. It's a simpler design, but basically it's a piece of ground PCB with the coaxial cable just behind. I don't know if you see, you have the metal grounded and the little piece of antenna coming, and you have, maybe with the reflection, you can see these small 4 corners. These actually are 4 patch antennas, one straightforward to each other. Why they have 4 and not just one big? Because the frequency band of this antenna is for 5.8 gigahertz. So each one needs to match the frequency band. So actually, we can just have one of these small squares and it will be a perfect patch antenna. What we have here is actually 4 patch antennas in just one small device package. Just to make it this a little bit funnier, I added some DIY antennas, because antennas is basically pieces of metal that you can just, with careful, you can make them. You can make what is called a cloverleaf antenna. Cloverleaf antennas have a really spherical pattern and they radiate well in all directions. And you, as you say, you only need copper because it has really low resistivity and a coaxial cable. And by measuring, for example, if I want to emit for my Wi-Fi, at 2.4 megahertz.
It's in megahertz.
Sorry. Oh my God. Actually, this is the length of the wires that I will need to cut through. So with these simple calculators, you can actually measure the piece of wires and shape them. Why you twist them in an angle? This is about polarization and polarized and non-polarized antenna. We will see what is. This is a small guide on polarized antenna. Super slow. Okay. Sorry, something that I forgot completely to talk about is the range, the power. With electromagnetic fields, duplicating the power doesn't duplicate the distance. It's actually something, it's an inverse square law. Duplicating the power of transmission doesn't increase the distance. So actually, having a transmission, let's say, device, for example, like this, that is a low frequency transmission device of 1 watt, may have 5 kilometer range. But increasing to 2 watts is not going to increase to 10 kilometer range. It's going to increase more or less to 6 kilometer range. So actually, we don't have more range by just increasing the power. A way to increase the range is by changing antennas, increasing the power, and working with the frequencies. Why we just make really high power transmission devices? What happened with really high power transmission devices? Heat. You need to dissipate a lot of heat. And actually, the amount of power that you need to increment, for example, to change to 10 kilometers, maybe you are multiplying by 50 the amount of power. That means there's no physical way to dissipate the amount of heat produced by the transmission and receiving chipsets, and by so they burn. And actually, they don't exist. So something that you need to really account for is first transmission power, frequencies, and antennas design. Patch antennas, for example, something if you want to have fun as DIY is how to increase your range with a Coca-Cola can. Why? Because you have a dipole antenna you can isolate the back of the antenna with half Coca-Cola can, just like this, and this kind of thing works. It's physics, it's not magic, and it's not scams. By actually isolate the part of the antenna where you don't want to receive information and make it more sensible, as you have less interference or less noise or frequencies, you make it more sensible to this direction. And this kind of thing works a lot. I have put also more links, and actually one that works really well and works really well for Wi-Fi is the Pringle can antenna. That is actually matching an antenna perpendicular and isolated just to have one directional tube. Of course, with this antenna, you will only transmit more or less in a 15 degrees, let's say, cone of transmission. But with this, if you put it in your rooftop and you orientate properly, you can easily, if I have this in my rooftop and I point to Óscar, Óscar, for example, lives in Universitat, I live on Gracia, really probable, Óscar will be able to connect to my Wi-Fi network just with this hack. You increase a lot the range. I recommend you to try, it's really funny. Actually, last year in class, we did it and we assembled a telemetry network with CAN antennas through the lab in the different floors, and it worked quite well. It's a shame that this year we couldn't do it.
We will do something fun tomorrow too, don't worry.
So range, power, dBi gain. When designing a system, you first want to establish what is the distance you want to reach. With that, you have already a big clue of what frequency you want to use. Another point will be what is the data size and the data amount of transmission that you want to transmit through that wavelength. If you want to transmit a 4K video, obviously you are not going to transmit in a lower frequency. You need to increase it a lot. Another thing is actually, are you going to broadcast everywhere or you want to have directional? For example, police, the radios, these ham radios, they want to transmit everywhere. They just want to point every time in the connection. But TVs, for example, are really directional. So it's something that you want to work with the dBi gain. And when you buy and look for data sheets of the antenna, they always have this plan of dispersion, this gain dispersional map, one in the vertical and one in the horizontal, to see what kind of is the three-dimensional representation of the directionality of the antenna. They also state the dBi gain of the antennas. For example, this antenna says it's made of this material, has this weight, has this connector, is center frequency. It means it's tuned for 4.8 gigahertz frequency. When you work about standardized antennas, that is what we found nowadays in all the markets on the really industrial, a center frequency antenna works well at 0.1 gigahertz down and 0.1 gigahertz up. That means an antenna tuned for 5.8 gigahertz will be able to reach nicely to 5.7 to 5.9. Obviously, it will work better in 5.8 and actually in the center of the spectrum. But that's not always like that. And that's because of the noise of other frequencies. So for example, when you have different emission devices, let's say you have in your phone, you have Wi-Fi and Bluetooth. Actually, they use the same frequencies, but they use different protocols. Or for example, a way to reduce range, for example, you have a FM radio. If you put a device that is transmitting, for example, Bluetooth, AM radio is around 80 megahertz. Bluetooth is 2.4 gigahertz. They are really broad in the spectrum, really far away. What happens is if you have a really high intensity power transmission in one frequency, even if the antennas of this device, they are not tuned for this one, they are getting so much noise that this device is actually not hearing properly to this frequency. So actually you always want to have antenna dispersion and distance between the devices, and especially when you have a really low power device and a really high power device. For example, lower the frequencies, and this is something about hardware and how it's done nowadays. Lower frequencies devices, for example, 400 megahertz, that is a long-range device like LoRa, uses really a small amount of power to transmit, and actually uses around like 20 milliwatts. But for example, a Wi-Fi transmits in 200 milliwatts. That means 10 times more the transmission power. But if you have a LoRa next to a Wi-Fi router, it will not receive well, because one is tuned for really high sensitivity to sense really a small amount of powers, and the Wi-Fi is transmitting a lot. So it's making a lot of noise. So, and you have the bandwidth. Actually, I was wrong. This antenna is telling you that it has a really broad spectrum. It's setting here. And the antenna in this datasheet is stating that has a 2.5 dBi. With this, we can say that with this antenna has low sensitivity, but it's really omnidirectional. And actually, this antenna is tuned exactly for this frequency. Axial radio is another type of the game that is much more complex to explain. And we have polarization. So when you want to design a device, you need to take into account a lot of different things. One is the power of your transmission device. Second is the frequency. Third is the antenna sensitivity. How sensible and what is the ratio of power by transmitting that is able to reach. That is also, in this case, you are using the antenna for transmitting, it's like that. It's also measuring the gain. After, you want to have 4, the sensitivity of the receiver antenna and the link margin. That means the amount of frequency wavelength that you can lose. The frequency, the link margin, is usually calculated at around 10 dBi, 10 dB. And this is actually the distance that you are able to reach with your TX antenna, RX antenna, transmission power, and receiver sensitivity. Actually here, for example, we have a calculator. For example, if the VTX power is 23 dBi, that usually the transmission power of the devices is not given in dBm, it's also given in watts. But there is also calculators to translate the watts of transmission to actually the dBm. And this is, for example, equivalence of table. For example, a 200 milliwatt transmission has a dBm usually of 23.01. So by stating this, this is a quite standard. This is, for example, like the fast connection of your modems. DVX antenna, usually the Wi-Fi connections have 3. VRX antenna, sensitivity. Actually, the phones don't have a higher sensitivity usually. Link margin, calculate. So at this frequency, not through Wi-Fi protocols, but at this frequency, Wi-Fi is able to reach 2.7 kilometers. What happened? We don't have this because the Wi-Fi protocols using pair connection and packets that they don't allow this kind of connections. But the physical limit of the frequency of 5.8 gigahertz is actually 2 kilometers.
But on your router, usually you see 5 gigahertz and 2.4. No, what's 5.8, or is it something else?
No, they state 5, but it's 5.8.
Okay.
It's actually it's not legal to transmit in other frequencies. They just state 2 and 5 just because it's easier and people really doesn't know what is one thing or the other one. So what else? So we have the omnidirectional, directional, and this is, for example, let's say the perfect antenna. This doesn't exist at all. Usually it looks more like this, like the donut that I say, a normal standard dipole antenna. Frequency spacing. What happened, for example, if we have 2 people talking at the same time? We don't understand each other. But what happened if one It's a small baby that is crying, and we have a grown big guy that talks like that. It's easy to understand the difference between them, no? And what they are saying.
Like when there's a cuckoo and somebody talking.
Exactly, the same. So why? Because they talk in different frequencies. And when you have radio frequencies, and usually, well, if you just download a Wi-Fi scanner on your phone and you see the amount of frequencies that you're emitting, more or less, each of us will receive around 50 types of frequencies in different bandwidths all the day. So what happened? You have a lot of people talking at the same time, and sometimes they use the same frequencies. So what you want to have, like what's called frequency spacing, because if the frequency that this device is talking has another device talking in this frequency, if we're going to produce interference and electromagnetic noise, and it's not going to be able to transmit and receive properly. So usually this is a standard, depends on the country, but the European Union has the same standard all around. This is a long time ago, that you have able to transmit in some kind of frequencies. And actually it's not that you are not able to transmit in this one, but legally you should not, and it's illegal to transmit in these frequencies. And this is those frequencies that are isolated, so actually they are allowed to have better reception on each individual channel, accounting that you will lose some channels. Let's say you will have less channels to transmit, but each channel will have cleaner information, advice, so it will increase the range without having to increase the amount of power and that you are transmitting. Because we cannot forget that what we are transmitting is actually electromagnetic fields. And this is not something about paranoia, but humans, we absorb electromagnetic fields. And that's why, for example, when you go to an RX scan, you protect, in case of the girls, they protect the internal female reproductive apparatus, and the male we product with some like lead parts, because the biological humans and animals can only receive until a certain amount of radiation at different wavelengths without damaging the cells. So actually, the lower radiation electromagnetically that you receive, the better. That's why you have some standards, and legally in Europe, for example, you are not, in general, you're not able to transmit higher than 200 milliwatts. To actually don't allow that your absorbance at different wavelengths is not too high for your cells, and you will not get damage on your cells. And that's quite important. For example, in the United States, they can transmit 10 times more power on the Wi-Fi spectrum. One of the reasons is because of how people is dispersed to the country. In Europe, we have a lot of people living really close in big cities, and most of the country is not country anymore. Like wild country is controlled country by the humans. The United States have big land areas without any kind of population. And by so they need to increase the power so they are able to reach further away. This depends a lot of the country. I know the United States case because I usually use American case devices. For example, that's something that, curiosity, when you buy a DJI, a drone, DJI emits in 2.4 gigahertz and 5.8 gigahertz. When you connect, the first thing you will do, the device, is actually check your GPS on your phone to put the transmission power mode according to your country laws. And that's, if you look in videos and you know people in the United States is able to reach like more than 10 kilometers with a normal DJI, and in Europe we don't reach more than 2, because the transmission power legally is lower down, not hardware, but on software to make accordance to the law. And actually you can hack it to increase the range, as always. So for example, when you work with a frequency and you have a friend or neighbor that's also talking in your frequency, you want to have what is frequency spreading, that sometimes, for example, in case of the ham radio, you don't have this problem. Legally, you can transmit in all the channels. But what you want to take care is you want to have a frequency breeder or accordance or agreement with other users that if you use this frequency, you are not gonna transmit in the, there is not gonna be anybody between all these frequencies. That is the low and the upper CB. So are frequencies that you're gonna let free so you don't have interference, and by so you can reach better range. I know this is a little bit dense on frequency, it's a little bit annoying, but I think it's quite important to understand these kind of things. For example, a clear example that you know is you have AM and FM radio. What is the biggest difference that you can hear? Is the quality of transmission. No? One sounds much better than the other one. Because AM radio is for amplitude modulated radio frequency. That means we not only change the frequency, but we are also changing the amplitude. That means by transmitting at different frequencies, we are transmitting with more and less power at the same time. We don't have a regulating power output. With that, that means that AM radio always gets better coverage. Why? But with lower quality. Because we get more gain, and by so we can reach further. But in this point of the wavelength, we don't reach. And that's why AM radio has this noise, because we are not receiving constantly the same amount of power of transmission. With the FM, is modulated frequency. Is all the wavelength has been accouplated, so actually transmit at the same amount of power. So the data transmission is much more uniform. This is just about curiosity. For example, radio jamming works more or less in this concept. You are transmitting with a frequency. How to avoid that the receiver gets your data, but actually producing the same, a different amount of data transmission, but exactly on the same wavelength, and you are increasing not only with more power, but with more amount of packets that doesn't make any sense. So actually the receiver is receiving information for the frequency that is being tuned, but is receiving mismatched information. And you have accouplation of frequencies. That is something that has to do with the polarized and not polarized antennas. So for example, if you have a frequency, this is one emitter, and you have another emitter that is the same frequency, these frequencies inside, they have peaks of transmission. That is the data. So you have two wavelengths that are being transmitted, this wavelength accouplated. I'm going to redraw it. I'm doing really bad. I'm going to change. So if I have another frequency, another transmission that has the same wavelength, they accouplate. But what happened is maybe this wavelength has a peak here and a peak here. So what is the output result of these two wavelengths? It's actually the middle. So you are not getting the original data and you are not getting the other wavelength data. So actually you get what is isolating and is jamming. And you do by transmitting at basically the same frequencies, but different amounts of data. Jamming is something that is broadly used nowadays. It's illegal actually to do it as standard citizens. But you have seen maybe probably this, especially now with the drones, that they say in the TVs, nah, they have a drone for drones. Actually, it's not a gun, it's a radio frequency gun. What it's doing is jamming in a super big, broad spectrum, all the frequencies. So it's basically it's a barrel scanner that jams a big broad amount of frequencies. So actually the drone loses connection and by so crashes or lands. And this actually, all the official cars from the politics, like important people of the government, usually they have jamming devices in all the cars to avoid, for example, like bomb activations and this kind of things. So for example, you have a remote activation of a bomb because usually you don't want to immolate yourself. You want to do it wirelessly. They cannot actually, the receiver cannot actually sense the transmission activation. because there are so much noise in that same frequency that is not be able to discern between what is the real signal and what is the jam signal.
Do you know how broad they are, these jamming guns?
Actually, the jamming guns are usually really directional. But for example, the ones that are in the official cars, they are not really far because they have a really low DVI antenna, but that protects really well around. So how to draw this? So for example, clear all drawing. So for example, you can have a little guy here transmitting, and you have the official car. So the antenna that they will have is going to be usually a kind of monopole antenna that maybe has the kind of shape of donut on receiving, but this is not be able to reach here. What happens is when the signal gets here, there is another wavelength that is transmitting exactly in the same, so they accouplate. So this wavelength, is accouplated with this one and is being jammed inside the sensitivity area. And by so, this is not be able to receive the explosion trigger. And actually, this is how the cell phone canceling works, like the headphones canceling works, but with sound. Actually, the noise canceling headphones, they are not taking away your sound. Actually, you don't feel it, but they are canceling by making exactly the same opposite noise to the same frequency. With the antennas, we have antennas connections. And luckily, this has been a standard, and we have more or less 4 types of antennas connection. We have the most standard, that is the SMA antenna connection. That yes, always they are kind of goldish. Usually it's not gold, it's kind of semi-material but gold coated. That you have the internal antenna and the coaxial, let's say, isolator around it. A SMA female antenna has a little tip, and this is actually a female. Why? Because this is the male that gets inserted into. There is the opposite, that is the, sorry, it's not SMA, is RP reverse SMA, that is actually the male has also another male inside. So usually when you buy antennas, it's something that you need to take in account for, and it's actually quite important. That is, if you have a SMA or RP SMA. We have UFL connectors. This is the kind of connectors that you might find inside most of the electronic devices. Tick, tick. Why? Because these connectors are easily to embed in any PCB. They don't use a lot of space because they are really small. What happened with these kind of connectors is they have a life cycle of only 20 connections because they basically work with a small clip. UFL connection PCB looks like this, and it's something that you might find in here you can see it's kind of the same size of a resistor and has a small clip. It's more or less like a lot of laundry clips, but on a really small scale. And because they are really small, they don't last a lot of time. So this kind of connectors is nice if you want to save weight, but you are not able to disconnect and connect a lot of times. On the other hand, these connectors are really sturdy. It's really impossible, almost impossible to break them. What happens is they are big and huge. There is a third type that is the MMCX connector that now is a mix of both. It's neither an SMA, neither an UFL. Works with a clip connection, the same as the UFL, but has half the size of a SMA because it doesn't have the threaded rod. So basically, these kind of connectors just clip inside. They are good, they are easy, and they are reliable. Polarization. This is something, what happens when you want to transmit. You have 2 transmission devices, that are transmitting different amount of different data in the same frequency. You can have jamming between the devices, no? What we can do, for example, most of the antennas are what is called linear polarized, that they emit linearly in one direction. Let's say for example, in the normal of this will be the XY plane. And if you orient the antenna in the other direction, the normal will be the X, and you are transmitting in the ZY plane. So when you have a linear polarized antenna, you are transmitting, kind of changing how the wavelength is being transmitted. By making antennas that are tilted, like these ones, you are not transmitted in this direction. You are transmitting in this direction, but you are also transmitting in this direction, and you are also transmitting in this direction. So that means the frequency is rotating. So what you make with a polarization is you make a combination of these emissions and you polarize. So actually the frequency is not linear, it's three-dimensionally. It's not anymore 2D. You are polarizing and making the wavelength rotate. And that's good because you can rotate right hand or you can rotate left hand. So actually you can have two emission devices, one rotating in right hand, one in rotating left hand, and they will not jam each other because they cannot accouplate themselves. And that is something really useful when you have a lot of devices connected and you don't want to have noise interference between them. For that, you use this kind of antennas. And this is widely used when you want to have really isolated wavelengths. Something that is really important is the receiver and the transmitter, they need to have the same polarization. You cannot have a transmitter of right-hand polarization and a receiver of left-hand polarization. Actually, it will not be able to transform that wavelength and receive it through the antenna because it cannot accouplate with the antenna design. Why you want to do this? There is something that is called multipathing. If you have a transmission here, what happens when you have a wall? This wavelength, part of it is going to be dissipated or go through it. Another part of the frequency is going to bounce back with kind of the opposite. It's bouncing back in the opposite. So when you have a receiver, little antenna tower, this is receiving this frequency and this signal, but it's also reading the refraction of the signal by any kind of object that is around it. And what is happening is you are getting accouplated signals, but that they are opposite to each other. So if you want to reduce this kind of problem of interference of reversing signals, you want to polarize your antenna. Why? Because this is rotating, let's say, like this. But when you're bouncing back, you are getting the opposite wavelength, but rotating left hand. So with that, you can avoid and only be able to listen here and not listen to the other opposite wavelengths. And actually, that's one of the reasons why you use polarized antennas. Here. So you avoid this kind of noise that now we don't see because this is just because analog signals. Actually, this is something that for data transmission, but we don't see, but I posted through the page a few videos of what is multipathing and not that is interesting you to see. For example, pixel antenna, range path loss calculator, frequencies, AM signals, jamming guns, etc. Where is article polarization? It's not here. I posted. Wait for a second. Range loss, DBI, Boston antenna. For example, it's not exactly the same, but this is about wavelength penetration. I'm just posting analog video signals because it's the easy way to understand. Because looking at zeros or data packets on a terminal is not that clear. But for example, this is the difference between same amount of transmission power, but different frequencies. This is 1.3 gigahertz. Sorry, there is one that is really clear here. So for example, in analog video, we can really see, you see these small blinks that you are getting. Actually, this is the refraction back from the trees because they are bouncing back the signal, and this is the multipath. In the moment 5.8 gigahertz actually accopulates really well with the leaves of the trees. And you see, in the moment we get inside the tree, we almost get all the connection loose. So physically, we are not receiving the frequency. Meanwhile, just by reducing 1/4 of the frequency range, we can still get a lot of image. You see, this is multipathing, and this will produce a lot of data packet errors. What happened is we implement software solutions. One of the software solutions we implement is something that that Bluetooth does. Bluetooth emits at the same frequency that the Wi-Fi, almost. Not exactly, but almost the same frequencies. What happened, Bluetooth uses what is called a FHS protocol. FHS protocol is frequency hopping protocols. How to explain this? Yes. This. So Bluetooth is all the time scanning the whole range of frequency that is able to transmit. It means from 2.2 gigahertz to 2.5 gigahertz. It's all the time checking how busy are all the channels. And when it's talking, for example, through a Bluetooth device, for example, an audio speaker, I don't know, an audio speaker, they are communicating all the time. And the master of Bluetooth, because in Bluetooth there is always a master, the master is scanning all the networks of that frequencies range that is able to transmit. When finds that the channel is transmitting, for example, 2.3 gigahertz, is noisy, it means there is noise, it says, okay, speaker, we're going to change to channel 2.5 because there is no noise. So it's called frequency hopping. So Bluetooth protocols, they have usually really good transmission data flow, because in the moment that they are seeing that there is a channel that is noisy, they automatically change all the time. And actually, that's why Bluetooth is paired. Because if you don't pair, this one doesn't know in which frequency this one is emitting and this one is not. So when you have a Bluetooth protocol, you always are paired because you need to change channels all the time. That is a protocol that is actually really good because it's the most stable one, because you are changing channels all the time actually to see which one has less noise. For example, something that you can do, for example, at home, just to see to get better coverage, is to download a Wi-Fi analyzer and see which channels are more occupied than other ones. Sorry, I want to see one that has the frequency bands. This one. Can I see lower? Yeah. So for example, channels, Wi-Fi channels are between 1 to 13. And depends on the house and the distance, you can actually say, okay, if I'm this guy, direct HP office, actually this is, I'm in the worst channel that I can be. Why? Because it's already busy with 2 other channels, so I'm making a lot of noise. If I change my channel to this one, I will have a cleaner space channel, and I will be able to receive much faster data because I will have much less packet lost. And it's actually something actually that is really important. What happens is Wi-Fi doesn't do this. Wi-Fi protocols doesn't do this all the time, because you connect and you get a password and you get a token of authentication. That means you are able to connect, but you are not changing the Wi-Fi channel all the time. On the other hand, for example, Bluetooth is changing all the time. It will be changing from here to here. And if another Bluetooth device connects and uses the same frequency, it will change to another one that is not in use. And this is, for example, one of the biggest difference between Bluetooth and Wi-Fi.
And you can, but for example, in case of a static, for example, the router that you have in your house, you can set up in the router which frequency do you want to spread out your house Wi-Fi.
Yes.
Okay.
Yes, and actually it depends on the modem that you have, your emission device. If it's a good one, it will kind of automatically change the channel automatically. But most of the devices, they don't do this. They just assign a channel. So I always recommend that, especially at home, that in the city, you live in flats, you have a lot of networks around, you do like each 3 months a Wi-Fi scan to see if a new neighborhood has get a new modem, and by so it's changing and using the same channel as you. So your Wi-Fi is slowing down suddenly so much, probably someone is using also the same channel as you. And by so you are losing a lot of data connections. Or maybe just one just got your password, but I don't think. But
do you need an specific hardware to do a Wi-Fi scanning, or is it just more?
Just with the phone. There is Android and iPhone apps, they do automatically. And one of the things they tell you is this. For example, this DBM. This actually is the DBM loss strength. So actually, this means you have more sensitivity, because it's the receiver sensitivity. It's the DBM rate of the connection. That means that it's able to receive more information and is in a more sensible mode because there is no noise around it in this channel spectrum. And actually, one of the things of changing between 2.4 gigahertz and 5.8 gigahertz in modems is actually that 5.8 gigahertz is a much less busy band. Not all the routers transmit. For example, in this image, 14 channel is actually a 5.8 gigahertz. Actually, here there is nobody. So in this case, this house, there is nobody transmitting in 5.8 gigahertz. So if you transmit in 5.8 gigahertz, you're going to be alone. And by so you're going to get the fastest data reception because there is no data loss because of jamming of other frequencies.
Hello, and because of the frequency hopping, Bluetooth is that slow, no?
Sorry?
Like you were describing the frequency hopping.
Yes.
Is this why Bluetooth is much slower than the Wi-Fi?
One of the reasons. Because physically they talk in the same frequencies.
Thanks.
Yeah, exactly. What happened with that is, as you are changing all the time frequencies, when you change frequencies, internally, hardware, the transmission chipsets, they need to switch on and off to change the channels. Let's say you are resetting all the time. By so, you cannot have constant data flows. Because you basically have to turn...
Sorry, no, go on.
Yeah, just tell me.
No, I was just going to ask what happens exactly with the internet boosters, like los repetidores. O sea,
internet boosters, basically, they just receive the data and they transmit again the same data. But they...
Okay.
So, internet boosters. So if you have the antenna here, you are transmitting, this strength is reducing by the distance, and it's reducing with a graph like this. Let's say the amount of power. So here, you are not receiving half the power of here. You are reducing actually a lot the power. The amount of data here is really much smaller than here. So what you do is you put a booster. So what we do is actually augment again the power length of the same frequency. So the amount of power that you reach here is more or less more stable. So actually the power transmission will be more or less like this. But basically they boost the signal, they repeat the signal. So it's important that this guy is in a proper location that receives enough power, so there is no package loss. Okay, so that's one of the frequency hopping is why Bluetooth has always master-slaves connections. I have put some examples of Bluetooth connections, and actually the protocols that they use over the air really depends on the device you use. Most of the devices we use, for example, the Bluetooth, this is, I don't know, I have a Bluetooth here. I don't know, for example, I have this one. This is a HMM protocol. This is what they call serial air transparent links. That means these chipsets and microcontrollers and transmission devices, we just connect, for example, most of the time, sometimes I2C, sometimes SPI, sometimes the more or less is serial, that is RxTX, and we don't need to tell what kind of protocols uses in the air. They have their own encryption protocols, and it's defined by the hardware. For example, Bluetooth is always FHSS. And the good point is we never have to manage that. You can get inside with RxTX, and these devices, you can configure them. So for example, Bluetooth has what is called an 80 command list, and most of the serial connections for radio transmission, they use 80 commands. Most of them, not all. So with that, you can check what are the basic parameters. You can check the version of and update the firmwares, and you can reduce the RFF power. So actually, most of the devices, you can change the transmission power of them. And also you can change what is the UART both over the air speed. Because these devices, they can talk, for example, at 90,600 speed over the serial communication to, for example, your Arduino, but over the air, they can talk at another completely different baud rate. And the baud rate is determined by the frequency that you are speaking to. For example, you cannot talk at 115,200 baud rate with a 30 megahertz frequency, because actually you cannot transmit that amount of data. It doesn't fit in the frequency. So usually lower the frequency, lower the over-the-air baud rates. And this is, for example, to define the standard for Bluetooth, like the HH, for the Arduino Bluetooth, you can easily find the HC05, this kind of super cheap chipsets. The difference between this one and this one, that actually they look the same, is one of them can be master and slave, and the other one could only be a slave. So if you want to create a network with different one of them, you need to choose between the HC06 and the HC05. I don't remember one right now which one is this one. You have the HC011, sorry, no, HC10, I think. Wait, HM10 Bluetooth, yeah. That actually is the newer version of the same one, but uses a standard protocol of Bluetooth 4.0 that is able to transmit with a better frequency hopping and with a higher data rate, and also with lower power consumption. That is something that you usually look for with Bluetooth, having low power consumption on the transmission. Because the power consumption of these radio frequencies doesn't depend only on the frequency they are talking, and the transmission power that you are emitting, but also on the amount of processing data that you need to talk with the protocol that you want to talk. For example, Wi-Fi protocols needs a lot of processing power compared to Bluetooth ones. That's why, for example, your ESPs, I don't know, where is this? Or your ESPs have more or less a power consumption of 1 amp when they are transmitting and receiving data. But on the other hand, for example, with the same amount of range, the same frequencies, but just using different protocols, a Bluetooth consumes in average like 50 milliamps. So it's something really important when you want to have a standalone and battery device. So it's something that you need to take into account. They are devices that talk in the same frequency, but they talk in completely different protocols, and by so it changes completely how they interact. You have, for applied case of Arduino and Arduino, you have the NRF24 modules. These modules.
Sorry, Edu, one question. Is there any reason why they come covered in plastic? I simply...
No, just to avoid that you put water on them.
Okay, so I should better let it covered with plastic?
Yes, plastic for the antennas and reception really doesn't make a big change unless a really dense plastic.
Okay.
So for example, the NRF24 is a device that actually uses standard telemetry protocols. It means it doesn't use neither Bluetooth protocols, neither Wi-Fi protocols. It talks what we call telemetry protocols. It means we just can send live data, just send and wait that someone listens. We can have confirmation of packets received or not, but it's something that we can implement in the software. It's not done by the hardware. The hardware doesn't care at all. So for example, these small chipsets that they look really small, actually they look really similar to the SP8266 in the shape. They also transmit 2.4 gigahertz and 2.5 gigahertz. And actually the power transmission of these devices is really small. What happened with these devices? This is the third type of device that talks in the same frequencies, has the same amount of power, but actually this one can reach further. We have seen before that we have calculated, I don't know if you have it open, we have calculated that we can transmit more or less at this frequency until up to 2 kilometers, no? We just calculated with a proper antenna, we can reach 2 kilometers range in 2.8 2.4 gigahertz frequencies. What happened? This is a open transmission protocol, and actually the protocol of transmission and how we communicate the data is based on software. We define it. By so, doesn't have to implement so much hardware working, and we can transmit freely. But what happened? We are able to transmit to 2 kilometers, but maybe at 1.8 kilometers, we only receive 20% of the total amount of packets of data. You understand? So what happened is, in that case, we need to work a lot with having checksums. For example, something that is called a transmission protocol. A good way is, for example, Andrea was sending, for example, the data, your data, with an L. So you know the kind of sensor is, no? So a good way is to implement it is by using checksums. So what you do is send number of the data transmitted. So one device is transmitting, okay, this is my first number. It states 1 and your information. With the receiver gets the 1 and information and is sending, okay, I received 1. When the transmitter receives, okay, I received 1, sends 2 and the data. If by somehow this guy sends 3 and the data, and this one answers 2, it's gonna, okay, this guy has not listened what I said before, so I'm gonna repeat the data. So by so you are making comparisons of what package data you have received and which ones not. This device, you can implement protocols like this, and it's nice. What happened about and I don't especially like it, is it's really annoying in wiring because we need to use SPI protocols for it. And by that, we need to use protocols to include this. Last year, we did an example on actually connecting each student, which is on NREF, and connect it all through a network. And actually, they make kind of a small WhatsApp with the Arduino terminal. And they were talking all to each other with this small 2.4 gigahertz network. We have some protocols that devices that this radio frequency that is a HC12 that is actually half duplex wireless serial. This is really similar in this communication, but is half duplex. This one is transmit receive. That means this device is only able to transmit, and meanwhile it's transmitted, is not receiving anything. It's not listening. So it's important when you want to have, if you know you are making something that you need to have really fast interactions, you don't want to have this kind of hardware connections, like transceivers, because this works more or less like a walkie-talkie. That's why it's a transceiver. So when you talk, you cannot listen. What happened with this one, for example, is a half duplex. That means we can read and transmit at the same time. That is quite nice. I like a lot this one because also talks at 400 megahertz. That means we cannot send a lot of data. When I mean lot of data, and means I'm talking about videos, movies, or music. Like for the kind of information that we usually talk with in Arduino and the kind of projects that we do in the Fab Academy, is more than enough. This one can reach up to 1 kilometer with just this simple city antenna. This is a 1 centimeter size antenna. If you change this antenna by a patch one, you can easily increment this to 20 kilometers. And this thing costs, I think, €2. And it's quite good. And actually it has really high sensitivity. But the sensitivity is also determined by the baud rate that you are talking. So higher the sensitivity you put it, lower the baud rate you have to talk with. You have to the speed you have to use. But it's really good. And it has half duplex, and it does in the internal protocols. That means we don't need to manage everything. For us, talking with this device is talking exactly the same as with the FTDI. I love this device because it's super easy to use and it's really powerful. And we configure it also through AT commands, the ones that we checked before. So basically, for example, a connection between two Arduinos will be like this. The TX told to the RX, the TX told to the RX, and after they can communicate with the half duplex protocol between them. If you want to, the good point of these ones is they are called serial transparent bridges over the air. So the protocols that you use to check if you have received the proper data no is implemented on you. And these are some examples of how to use these ones. And we have Wi-Fi. That Óscar, I don't know if Guillem is going to explain this, you, or we can go together.
No. Guillem is going to talk about OSI model. That is like the standards that we implement in this, but not. We can do this one together now, or maybe tomorrow. Because it's already 2.
Okay. Maybe tomorrow. Okay, so that's more or less an overview of radio frequencies and transmission. I know it's much more hardware related, but the hardware related in over-the-air transmission is actually really, really, really important. So for example, just to give you an idea, something that you have used, this guy proved that the Arduino that you have with a proper antenna, obviously like direct air connection, can reach 10 kilometers. And actually I think it's really, really surprising how like it's more or less well documented, and even has an article on Expressive that explains a little bit deeper what is happening, etc. And you see, it's using just a standard TV antenna, because the standard TV antennas, they are rated for different wavelengths and they work well in more or less all the wavelengths. So actually this guy at some point, let's see if we can see in the video. Yeah, of course he was having a lot of data packet loss, but it was getting the IP camera connection for just changing the antenna. I think deserves just that you take a look at it, and it's quite interesting. And you see there is a lot of videos on actually how to make really weird antennas, more or less reliable, but works quite well. Usually they improve a lot. Antenna design is something quite interesting, and how to choose the frequencies. I'm gonna. So do you have any doubts or questions?
Yeah, I have a question. I don't know if you maybe passed through it, but how does the internet in Valdaura works? I mean, I know that they have like a shared Wi-Fi or something like between the neighbors, or I don't know if maybe Marco knows a little bit of what I'm talking about.
I think it's radio actually, because I had a meeting yesterday with Jonathan, and he had problem with the connection, and he told me it's because it's radio.
It's radio?
I'm not sure if it's LoRa or something, but I think that one of them has the internet and they have like a network between the neighbors. So, and they share the internet, like having one hub for it, but I'm not really sure about it.
Okay, if it's not wired connections, they will have like radio transmission. Obviously will be around easily like 100 megahertz to 1000 kilohertz. And that means they are constrained a lot of the data transmission flow. So even if the devices are talking at 2.4 gigahertz to a router, and the router receiving the data through a repeater that is being connected through another frequency, the big constraint or the bottleneck is actually the transmission rate of the radio transmission. So that's why maybe one of the reasons why they have like slow connection, because it's not that the Wi-Fi is not able to transmit or doesn't have correct approach, but the bridge to the rest of the world is slow.
I don't know exactly about Valdaura, but probably what they use is this network called Giphy. I don't know if you know about it. So let me show you this one. I put this in. Sorry. So I put it in the chat for everyone here. Okay, and it's like a network that basically you have a bandwidth on dedicated to these guys, and you have a series of antennas that send data to one another on Barcelona, and you can be just an end node, and you just receive to your computers or stuff at home, or you can have like a super antenna somehow, or a super node in which you are receiving and also repeating and sending to others. And basically in the rooftops of the city, the network is distributed by different users. And the idea is that you're not using a ISP, so an inter-service provider, but more like this type of model. And I'm not sure, but probably they have something like this. We have a node in Pabla, Barcelona.
Yeah, Wi-Fi.
And you can even become a member. I think it's super cheap, probably like 200, 250 euros for the installation, and then you don't pay anymore. Or you pay like a very little thing. And it's a community. I think the only thing is that if the internet goes down, it means that probably one antenna went down or things like that. But then users really want to keep their internet connection up, so they help each other and try to fix things when there's a problem.
Thank you.
I have one question for you, Edu. I don't know if you saw my email yesterday. I sent you one. But it was basically, I just want to make a bit like the last transceiver you talked about. But except I feel this one's a bit overkill. I just want to talk something between one end of my room to the other.
I read it, and actually I say, okay, I'm gonna answer like in class. I think it's
because it seems like I was thinking of literally using my TV cable and making my own internet, because I don't need to send data. I just want to know when one antenna is transmitting anything and receive it on the other antenna.
Basically what you want to have there is kind of avoid fake activations or fake readings of different things. So what you want to use is a kind of frequency that you are legally able to use, but nobody is using, or it talks kind of information that nobody is talking to. For example, just to get this small device is a frequency emitter of 1 gigahertz and 915 megahertz. That is the same frequency that the police uses. For example, this one is illegal to use in Europe. Another thing that they catch you, and unless they have frequency scanner, they don't care. But this one has really long range.
It's still recording.
Yeah, I have it. It doesn't mean that I use it.
Disclaimer.
Yeah. So actually, this device transmits very long range data, but even if I'm talking the same frequency as, let's say, the police, if I use it, I want to transmit probably like information of numbers, not audio transmitting protocols that they use with the radios. So actually, they are going to receive and have some noise, but they are not going to be reading my data. I'm not going to receive their data. So let's say, and your data is audio, because I don't have an audio decoder. And for example, something that in case you want to go for LoRa and low frequency band devices, you have to be careful, because, for example, the 900 megahertz devices, they get a lot of problems with the USB ports, because the frequency of resonance of the data of the USB ports is exactly the same. And that produces lump sum hardware noise when you connect through the USB to these devices, just as curiosity. And in your case, Benji, there is a lot of NRF modules that are really, really, really easy and cheap to have. And it's something that, for example, the ones that you have in your garage door openers, those ones usually they talk around 400 to 300 megahertz, because basically you want to transmit this click on 1 or 0s. They don't have more than that. It's not that complicated. They have more because they have a kind of serial key that they are transmitting, but they are basically a number. That's why they are so easy to hack. Those devices are really, really small, and basically it's just a wire antenna and a transceiver receiver chip. I'm gonna look for it. Like,
I wonder how doable is it to do your own internet, just kind of for fun, even if it's not going to be
talking. You cannot do it on your own.
No.
Actually. No. Okay. Why? Because it's, let's say, it's not an IT that is transmitted. So, for example, this project I was going to show everybody, but this is how to use a Raspberry Pi to transmit as an FM radio. Actually, just connecting a wire to a Raspberry Pi, you can transmit FM radio signals, and you can create your own pirate radio, just connecting a jumper cable. Why it can do this? First is the transmission power outputs of the Raspberry Pi is high compared to other devices. Second is the frequency of the crystal resonator of the microprocessor of the Raspberry Pi talks, if I'm not wrong, at 100 megahertz. So the clock, the GPU clock, for example, talks at 100 megahertz. That means it's able to make frequency modulated at 100 megahertz. And by so, it's able to transmit with a frequency that we are able to read with our normal radios. What happened, for example, with the 8010 44? What is the clock frequency?
16.
is useless, let's say.
Yeah, but if you want to do FM, though, if you want to do something that's useful. In my case, I just want to make something that says, "Hey, I'm on."
Yeah, but it's the devices, they need to have like the called a TX Direct chip that is implemented by hardware, and but at least I don't know how you can do it.
Because I was wondering, how do you use it? Do you just plug the antenna to a pin and then the pin receives some like voltage modulation?
Yes, for example, this I just sent in the link, super small. This is kind of the same that they have in the remote.
It's the same thing as before.
Sorry. These are, let's say, the simplest wireless communication protocols that you have. This by SOT, it means that everything that you do, like checking for messages and error, it needs to be implemented by software. Okay. They are really, really low power devices. So that means they don't create big electromagnetic fields, and by SOT, they create interference with other devices. They use really low frequencies. By SOT, even if they have low power, they can transmit far away, let's say far away, 30 meters around, and they are super small. And these kind of devices are everywhere.
And could you feed it loads of power, just like more? It's not what I'm planning to do, but because I was saying the project was to tell you that when I switch the lights on, it can switch the antenna on, which tells something else that it's on. But because it's plugged into the power, it could theoretically get 220 volts, which might be too much, but it could. Would it make it go way further? Even though I don't need it.
You mean that you don't program it, but you send this, let's say, a data height?
Yeah, or rather than feeding it with a microcontroller, the power, you feed it with the power of the plugs, which is way more.
But no, at least that I know, you always need to translate the 220 AC to DC at some point. So you will need a buck converter. No, not a buck converter, but it's AC DC converter. You have some things that they are really small, especially if you are talking about small power devices, but usually they are at least the size of a relay. I think the bigger problem in this project is actually that how to take the electricity from your plug, your switch, to power everything in a small package.
Yeah, that's what I was right.
Benjamin, if I was you, I will not even think about this. I will do only let's say a switch pocket device, no, a plug that what is reading is actually the light, ambient light. And
I thought about this as well, using my ultrasonic sensor to kind of like listen to. I have these two ultrasonic things to measure distance, but then rather than using it for distance, you use it to send like high frequency wave, and then with a little microphone.
No, I was talking about, for example, you can have different light sensors. One is measuring all the time, and you have a comparator. So, for example, if you switch on the light and it's light, there is almost no change. So it doesn't switch on the lamp. It will switch on the lamp. Because if you only have one light sensor, it will see that night and day, and it will not be able to discern. But you have you can see the light state change and make comparisons, and by so activating the light.
Yeah, cool.
I think it's simpler. Like
I did think about this as well. Cool. Thank you.
More questions about today's lecture, guys?
If there aren't any other questions, just a reminder for tomorrow. Laura was asking this. So tomorrow we will have a session, hands-on session. The idea is that we will do a network between all of you guys, same way, more or less similar to the one that you did at the beginning of the course in MDev with Victor and Guillem. The MQTT, Node-RED, this type of thing. But the idea is that we will do it remotely. So I have a Raspberry Pi ready here, right on my desktop, and I will send you instructions of what to do for tomorrow, so that we don't spend time on the setup, but you can start working on the code and this type of thing. So two options, and I will send this in an email, don't worry. Option one is that you have Wi-Fi compatible chip, like a ESP32, ESP8266 or similar. Option two is that you don't have that, but you have an Arduino that and a USB cable that can talk with your computer, and that your computer can execute Python code or any other code that you make. I'm gonna prep a Python snippet for you. If you want to use something else, you have to boil it yourself. But I will give you a Python example. And the idea is that you read the data from the Arduino and send it remotely using MQTT, using a server and topics that I will send you this afternoon in an email. Okay. And then tomorrow, the idea is that we will make a dashboard with either your sensors readings, or I will send, for example, Antoine's sensor reading to Anissa and Benjamin's to Edu and stuff. And each of you will be sending and receiving data to each other. And for example, you can then map the readings that you get from the network to an LED and turn on and off based on these type of things. Okay. So that wait for an email this afternoon and get ready your Arduinos, Pythons, and these type of things. And see you tomorrow at 10. Okay.
I still have a question. Is the satellite antenna is also working like this, like the same principles, or it's kind of different, bandwidth that they're working with?
What do you mean the same principles?
Like the satellites that we have like around the Earth, are they working the same principles, like sending through the like a magnetic field?
Yes, usually the satellite connection is really high frequency, really high frequency. Why? Actually, it seems that is the worst they can do. It's really expensive to put a satellite in like the, I don't know, like atmosphere, out of the atmosphere. What happened is once you get outside the atmosphere, you don't have that electromagnetic noise compared to what is inside. And even there is a lot of ionosphere and solar winds coming up, the distance that we are working is like the size of the Earth is like really small compared to how far the sun is. What you want to have is the highest data flow as possible, because unluckily we have more or less like, I think it's 30,000 satellites working, but we have more like 60,000 trash ones already. It's like we are full of trash. So you want to, and we used to actually host most of the communications of the world, and we are communicating really big amount of data packets. So actually we want just to have. That's why one of the reasons is we need a lot of power, and we need to have really steady connections. And we have the satellite tracker antennas, like they are really big balls that you can see sometimes in the roads, etc. That what they have is really focused antennas, and they keep track of the satellites all the time. And what you have, at least that I know, is we have like 3 or 4 big stations in the world. One is in Madrid, that is satellite trackers. Like let me explain you with a map. I think it's easier. Satellite heights above Earth here. There is one that is really far away. Depends on how far is the satellite. We need to talk in different ways. Yeah, I think it's this one. Yeah. So basically we have here the outer range. The problem of these ones is we can get with antennas only cover one area. And usually in these station antennas, you have covered like more or less 1/3. So actually what we have is we have a community that is one of the small things that the World Postal Community is to keep track of the satellites. There is one station, I think, near to Melbourne, one in Hawaii, one in the States, and one in Madrid. And actually between all of them, they keep track of the satellites, and when one gets out of the line of sight, communicates through it, through, for example, the Melbourne station, because of the ground wires connected to them. So let's say there is a Spanish satellite we will only be able to talk with it around 3 hours a day, 3-4 hours a day. What happened is what we do the rest of the time is alone, it's not working. No, what we do is like the Madrid station gets the radio signals from the Melbourne station, and after from the Hawaii station, and after from the California station, I think it is. And when it comes back again to the range, comes to the European. And we do that by changing all the world ones. But that really depends if you are close or far away. Of course, like the far away is usually for like external sightseeing of the universe and exploration. You have the GLONASS, Galileo, that this is different, like standard GPS location. That is how we locate things. And these ones are different standards of the world. This is the American one. Galileo is the European one that is newer. And actually you have now the new Galileo one. And after we have the, let's say, internal communication satellites that are from private companies, etc., that are really much closer. So they actually don't need to irradiate that amount of power. But the frequency of emission, if I'm not wrong, I think is super high. Yeah, it's like 100 gigahertz because we are sending massive amount of data.
Is it also so it can go through the atmosphere? Would it not go through the atmosphere? Does it emit in high frequency so it can go through the atmosphere? Because
yeah, also if it was really low, it will bounce back.
Bye-bye.
Okay. no questions.
Okay.
Hi
guys.
Sorry. When I am connected or creating a network with a Raspberry Pi and a computer with the Node-RED, it gives me a host local address and 0880 or something. Do I need to be connected to the same Wi-Fi or that address works everywhere? Or for example, with the app we created for the LEDs with the MIT App Inventor, do I need to be in the Wi-Fi or I could send that address to anyone and anyone could link those LEDs? It's like a personal address, that IP?
No, so that IP, for the Node-RED one, it's going to be local. You have to be on the same Wi-Fi network, but tomorrow we'll see how you can open, for example, access to your Raspberry Pi in this case. And even if, for example, I set up the server in Raspberry Pi, temporarily, I'm doing something called port forwarding in my router. That basically any input in income communication in 2 ports will forward them to the Raspberry Pi. And that's why you will be able to send data to my Raspberry Pi tomorrow, because you will send to like a public IP address, the public IP address of my router, to which I also gave it a nice name so that you don't have to put the number. I put it like netfablab.gcn or something like that. And that's how that we will do it tomorrow. And also you will be able also to see the dashboard yourself. In principle, I'm setting that part up. But for that, you need to announce it and let your router forward that information. Otherwise, your router just blocks it.
Okay, thank you.
So tomorrow we'll see this topology and we will talk about it also on Tuesday with Guillem. Okay.
Okay, stop the recording.